Hello and welcome. This is an exponential functions and sequences overview with several example problems. I'm talking close to about 40 of them, okay? There are quite a few. Hopefully it won't take, too long, but as you probably well know, I like to teach you the methods behind the madness as well as doing the steps themselves, of course. So here are the sections that will be covered. Properties of exponents will be first, then radicals and rational exponents, exponential functions, more like the equations, graphing them, things like that, exponential growth and decay, some models, some real-life models and understanding percentages with them, solving exponential equations, so like solving for x, and then these two are more the same thing, geometric sequences and then recursively defined sequences, though here we will also include arithmetic sequences. In geometric sequences, I think they ask you to observe and identify whether something's geometric or not, but that's neither here nor there. When we get to the bottom, you'll kind of see what happens there. Okay, I'm first just going to start by talking about these properties. I'm not going to say too much about them because it's all written here, and of course as this is a video, you can always pause, rewind, and do something like that, because actually these will pop up when I'm doing problems, because first I'm going to start with a practical method and then kind of make that conjecture that yes, this always happens when you do problems like these. So the first thing that I just want to mention before I even uncover these is really talk about exponentiation as a whole. Exponentiation refers to the number of times something multiplies by itself. Okay, technically starting from the number 1. So if I look at 2 cubed, yes, that is 2 times 2 times 2. 3 2's multiplied. I do like to say times 1, of course, though, because when we refer to the zero exponent or negative exponents, it's something really good to mention. And in fact, you know what? There is a property that's missing here, which is something to the 0 power. Anything to the 0 power, any non-zero number to the 0 power is 1. So there's another property to place in right there. Anyway, let's go over a couple of these things now. When you multiply by something m times the same thing multiplied by something n times, you're going to get a combination of the number of times you multiplied by itself here plus the number of times you multiplied by itself here. Okay, so now I use a lot of fraction ones here because we're going to have fractions involved as well. So when I do 3 to the 1/2 power times 3 to the 3/2 power, you're going to take the 1/2 and 3/2 and you're going to add them together. Now 1/2 plus 3/2 is 4/2. 4 divided by 2 is 2, so 3 squared is 9. This says a to the m power, all raised to the n power. Now this does not say that m is being raised to the n power. This says that a to the m is being raised to the n power. So when you multiply this thing by itself this many times, it's like multiplying those two exponents together, because this is already saying how many times you're multiplying a by itself, and then you're going to do it this many times on top of that. So of course that becomes a product there. That's what multiplication is. Now I have one here, and it's not really a distributive property, but you can kind of treat it like a distributive property. Same kind of thing. When a times b is multiplying by itself m times, then technically a is multiplying by itself m times, and b is multiplying by itself m times. Now I say distribute, but distributive property is really for multiplication, not for exponentiation. So if I use the term distribute, then you probably know what I mean. I might be doing these arrows quite a bit. I might say if you apply the exponent to them, something like that. Now, by the way, this is also true for division. So if I lead this down here, you can see the same connection. I'm going to apply the m both to the a and to the b. And then a is multiplying by itself m times, and technically this is 1 over b. So b is multiplying by itself m times, or 1 over b is, or b in the denominator. b can't be 0, of course, when you're referring to that. A to the negative m power. Now this is where things get a little weird, because negative exponents do not mean negative numbers. I'm going to say that again. Negative exponents do not mean negative numbers. If exponentiation, specifically in the positive direction, like the 2 cubed, refers to how many times you're multiplying by something starting from 1, then if you work backwards, then like 2 to the negative 3rd power, that refers to how many times you divide by 2 starting from 1. And I know this is going to look kind of weird right here, and I think I'm going to run into a few more practice problems with it. But if I divide by 2 3 times, that's equivalent to saying 1 divided by 2 times 2 times 2. All 2 values that are being divided are technically multiplying by each other in the denominator there. So this number is 8, and this number is 1 over 8, or 1 over 2 cubed. which is 1 over 8. So that's kind of the connection there. It doesn't give you negative numbers. Okay, negative exponents to from positive bases do not give you negative numbers. They merely do the opposite of multiplication. They do division. Now, a can't be 0 in this case, of course, again, because then you're dividing by 0, if that happens. Okay, this one ties a little more into the very top one, so let me point these two with each other as well. A to the m times a to the n, and a to the m divided by a to the n. When you multiply a by itself this many times on top, divided by this many times on bottom, and you want to end up doing a cancellation of multiples, of pairs of multiple values, then you're only left with however many results in the difference of doing the top minus the bottom here. And of course, I will be doing examples with these and you'll see them. But hopefully you're paying more attention to some of these on the side because I kind of forgot to keep doing that. Hopefully you can kind of read the notation and the syntax. This figure's kind of old. I actually did copy it over from an old video, so you might find this in different videos as well. So again, hopefully some of this stuff is making sense here. A couple more things I just want to point out when it comes to fractions, because you're probably seeing some of these. Why is 9 to the 1/2 3? Well, this is not half of 9. 9 to the 1/2 power also means the square root of 9. And, you know, like I said, we will jump into that as needed later. And this is 4 to the 1/2 power right here, which is then 2, because that's the square root of 4. So 3 times 2 is 6. 25 to the 1/2 power is the square root of 25, so that's 5. 8 to the 1/3 power, that's the cube root of 8. And that's 2. And 27 to the 1/3 power, the cube root of 27 is 3. So all these properties are laid out here, and I hope they're connecting pretty well for you. Okay, let's go ahead and start off some problems here. Simplify the expression, write your answer using only positive exponents. Okay, so we are actually kicking off with something that has division. It has a negative, all that good stuff. I'm going to see if I can first give you a very practical way of doing this. I know that sometimes this isn't the best way, and I know it really slows down the clock, but if you're having trouble with this and you end up calling this thing like negative 4x over negative 16 and have that as your answer, there's so much that's wrong with that we want to make sure that we address it. And maybe you start breaking it down a different way, or at least maybe this teaches it to you. Okay, for starters, I'm going to apply this negative 4 to the x and to the 4, but I'm going to apply it as far as exponentiation goes. So this is x to the negative 4th power divided by 4 to the negative 4th power. Now, again, if this is a practical approach, this is going to look kind of weird when I do this here, but negative 4 is in reference to how many times you'll be dividing by x. So 1 divided by x, whoops, divided by x, divided by x, divided by x, all over 1 divided by 4, divided by 4, divided by 4, and divided by 4. Okay, so all these x's here, they're actually being multiplied in a denominator. Now first I'm going to have these things in the numerator, like officially, like this is the denominator of the numerator. Then after that I'm going to take these ones and then I'm going to have these in the denominator of the denominator, multiplied together. And again, I know it looks very strange when I'm doing all that, but bear with me here. Okay, keep going on. Now, when I'm dividing something by something else, like this big division here, I could write it, by the way, x times x times x times x is just x to the 4th power. So that does make sense here. And then when I divide by this guy here, this is 4 to the 4th power, dividing by a fraction is the same thing as multiplying by its reciprocal. So that's why I'm kind of bringing this problem up like this. Maybe this isn't the way you'd officially do it. 4 to the 4th power, by the way, is 256. And I'm going to not use the calculator as much as you might expect me to. But I do have a calculator handy for me, and I will use it. But that's how I'm going to get this one started. Anyway, you multiply straight across now. 1 times 256 and x to the 4th times 1. Well, 1 times 256 is 256. And x to the 4th times 1 is x to the 4th. Now that's a lot of steps for this one problem, and there are shorter ways of going about it. So there is kind of a nice way of going straight from, I'd say probably this step down to maybe even this step right here. If you just kind of get this zoomed out look, hopefully the first one made enough sense based on the property that was featured. And again, I'll probably jump to that property in a different time when there's no negative exponent. But let's take a look at what happened from here to here. What happened was I have x to the negative fourth power on top, and down here I have x to the fourth power on bottom. So what happened was the negative turned positive. The negative turned positive in the exponent, but it moved down as a result. That goes back to that property, a to the negative m power equals 1 over a to the positive m power. So there's this whole equivalent of it because these are 4x's divided in the numerator, and that's equivalent to 4x's multiplied in the denominator. Okay, keep in mind that negative exponents do this, not negative numbers. And I'm just going to write this right here. I want to make sure you understand this, that negative 2 is not the same thing as 1 over positive 2. You should know that. I mean, you've known math enough your whole life to understand that if I pay you $2, that's not the same thing as you giving me 50 cents. Okay, exponentiation is different though because of its definition. The actual feature of this 4 being up here has to do with the number of times x is being multiplied, and that's it. The only feature of this negative 4 that you're seeing up here only has to do with how many times x is being divided, and that's it. So this number has to do with multiplication and division. That's what they have to do with. A negative 2 has nothing to do with the number 1/2. Okay, I want you to keep that in mind. Now, 2 to the negative first power is 1 over 2. That's true. Again, negative exponents not only do not lead to negative numbers, but they also, they do lead to fractions, whereas negative numbers in themselves do not. Okay, so this went down. Now 4 to the negative fourth power became 256, so this went up. So this guy, let's find a color I haven't used yet, just black. So this guy goes up and becomes positive. So this is 4 to the fourth power, which is 256. So in the end, write your answer using only positive exponents. When I evaluated this stuff, I had to make sure this became positive to do the true evaluation. And I think I'm willing to stick with that as well. The negative exponent stuff doesn't really, doesn't feel very welcoming to me, to be honest. It's not really the way to go. But so anyway, I'm going to be doing a lot of these moving down, moving up things whenever you have negative exponents there, including on this problem right here. Okay, so I'm just going to go ahead and move on. Y cubed times y to the negative fifth power. So if I'm going to do that moving process here again, I'm going to take y to the negative fifth power and I'm going to turn it into y to the positive fifth power by moving it down below here. If this is all over 1, well, this is now going to multiply by that 1, if you know what I mean. So y cubed is y times y times y. There's a 1 down there. Doesn't really matter. It's going to kind of go away here. That's 1 over y to the positive fifth power. So y times y times y times y times y. Okay. Here's what happens. As long as you have a multiple, a common multiple of a value on top and bottom, you may divide them and they will become 1. I know you hear a lot of people say they'll cancel out. That's fine. I like to try and kind of say both. More importantly, to specify they become 1, mostly because when all these cancel out on top and they're all gone, you don't want to think that there's just a 0 up there. No, there's actually a 1 up here now. So there's a 1 up here, just like there's a 1 on the bottom, and that 1 is technically multiplying with kind of nothing. Not by 0, but by nothing. Nothing's there. But there's just a 1 on top left. Now, there's 1 times y on bottom. So I have 1 over, this shortens up to be y squared. And that would actually be my final answer to this problem, 1 over y squared. Now, this was a more practical way of doing this problem. And if you think about it, if this was like y to the 23rd times y to the negative 25th, it would probably not be very nice to have to do 23 y's multiplied on top, 25 y's multiplied on bottom. But the idea still comes in play the same way. You will be canceling out pairs. Now, if there are 23 y's on top and 25 y's on bottom, a total of 23 y's would be canceling out here, and there would only be 2 left on bottom for the same reason. So what's actually happening here is subtraction. And if you think about what that last property was, the a to the m divided by a to the n, what's actually happening is you are subtracting the number of y's on top with the number of y's that ended up being on bottom. So if I do a different approach here and I just write this down here, the way that I would probably be doing this from now on, and again, remember this first set is very introductory, is, in fact, these are really the only 5 problems that we really do with simplifying. So it is probably good that I slow these down because we start to jump into the other sections after this. So this is probably good that you see these. And I can always point you to other videos if you need me to, other ones where I do more of these in depth and more complicated versions. Anyway, let's say that we redo this thing, and let's say I still move that y to the negative fifth down below, so it becomes y to the positive fifth in the denominator. So we're at this step right here. Now I'm not going to expand y cubed to y times y, or this with 5y's multiplied. Instead what I'm going to do is subtract, because if 3 are canceled out on top, then there are none left on top. If there are 3 canceled out on bottom, then there are none left on bottom. Or excuse me, there are 2 left on bottom. So we're going to do y to the 3 minus 5 power. That equals y to the negative second power. Now you don't want this to be your answer because the answer says leave it as only positive exponents. So I have a negative exponent here. If you follow along with what we did last time here, that would be 1 over y squared. So you still get the same answer doing that as you did the other way. Now, what if you don't want to turn this negative into a positive? What if you want to do it straight up as a product right here? Well, that's okay, I guess. You just got to know what to do with it. So let me move this all the way down and do one more approach. Here we go. Sorry, I have to kind of do 2 parts at once here. We'll have y to the third times y to the negative fifth. That's what that says. Now, if you're multiplying 2 items with the same base, instead of subtracting the exponents, you add them. Now, what does it mean? What does it mean to add a positive number with a negative number? That becomes y to the 3 plus negative fifth power. Now, something plus a negative becomes subtraction. So in the end, you get 3 minus 5. And it brings you back to this right here. Now we go right back to where we were. So y to the 3 minus fifth power. So no matter how you do this problem, you should always get the same answer of 1 over y squared. The first one really being the practical way. And you know what? By all means, if you have to do this, please do so. Just make sure you're expanding correctly. Make sure you know where this appropriately goes. And then just write what's remaining. Because these properties here hopefully are not so much a matter of memorization. Okay, I'm not a stickler, I'm a stickler for not memorizing. I don't like memorization. But the idea and understanding of exponentiation hopefully takes hold in the sense that you recognize what it is that's happening each time that you do something like this. And of course, I just jumped into a couple problems that did that. We're going to have a couple more like this and stuff like that. But if you can define exponentiation, then hopefully you can get a true understanding of what's happening. Not only that, but if you do this kind of thing enough, then you get what's called pattern recognition. You know, we made a conjecture this time and said that, okay, this canceled out 3 of them on top. That means there are none left on top, y to the 0, which is 1, by the way. And then it canceled out 3 of them on bottom, so there are only 2 left on bottom. So I subtracted 3 from 5, and I subtracted 3 from 3, and I was left with this. So again, pattern recognition, that stuff applies still. Okay, x to the 4th divided by x to the 7th. This one I get to kind of speed through this time. This is x to the 4 minus 7 power. Arguably this problem is possibly easier than this one because it's already kind of more set up for you. The exponents are already positive. Now this one turns negative for the same reason. 4 minus 7 is negative 3. And of course I'm going to leave it as a positive exponent. That'll become 1 over x cubed. Just like that. Now, I want to do something really quickly with this, though, because I felt like that was a very short problem in the end. What if this problem said 4x to the 4th power divided by x to the 7th? Just what if it said that? Well, this 4 is probably best to be written, understand this is multiplication, so this 4 is probably best to be written away from this mumbo jumbo like this. So even if it's written like that, it's best to avoid it because because 4 has nothing to do with this 4th power. Only this x does. 4 is being raised to the 1st power. 4 has its own little exponent right there. And of course, that's going to tie in a bit. Now, this x to the 4th minus x to the 7th still becomes, divided by x to the 7th still becomes subtraction, where you get 4x to the negative 3rd power. Now, what happens here tends to confuse a lot of people. You saw that before, when you have a negative exponent, it becomes 1 over the value. But this is not correct. This does not become 1 over 4x cubed. The 4 is not being raised to the negative 3rd power. Keep in mind, one more time, this is still multiplication. 4 is being raised to the first power. 4 does not move. That's the point of this. 4 stays right where it's at, and this becomes 1 over x cubed. So when you combine all of this, this would have become 4 over x cubed. And that would have been your final answer there. Not this, but this. When does this move down? When does the 4 move down? The 4 would move down if it was wrapped around in parentheses with the x. And I do believe we're going to run into a problem where we kind of have something like this, not with a negative exponent, but where we have something like this, because now that it's grouped, this is now being raised to the negative third power. You can either write it the way that I did before right here, where you apply the negative 3 to this and that, just like I did there, or I could write it straight up as 1 over 4x to the third power. Now this doesn't become this answer in red because remember 4 is being cubed. So 4 cubed times x cubed is on the bottom, and that would become 1 over 64 x cubed. So there are a bunch of different things here. This just ends up not ever being your answer for whatever's going on with a problem like this, parentheses or not. Either you don't have parentheses and you have a 4 on top, or you do have parentheses and you have a 64 on bottom. So you can see there's a lot of different stuff there. Now the original problem, I'm going to kind of ignore what was there now that you've seen that. The original problem was just this right here. And I'm going to go ahead and leave my answers 1 over x cubed, erase the rest so you don't advance forward and you see that answer and you're wondering why it was written. So I'll just go ahead and erase that. I'll box this nice and cleanly, and we are set. X to the 0 times y squared cubed. Okay. The first way I'm going to do this problem is not the way I would have originally done the problem, because normally my suggestion is to simplify the inside first if you can. What I'm going to first do is apply this 3. That way you can get a good practice and understanding of what's going on, that you can do this in any order that you'd like to, and you should still get the same answer. So I'm going to be cubing x to the 0 power times cubing y squared. Now, if I really did this in practical way, I'd say if I'm cubing x to the 0 power, I'm doing x to the 0 times x to the 0 times x to the 0. And if I'm cubing y squared, I'm doing times y squared times y squared times y squared. Now, there's a times in the middle because this was times in the middle. This is multiplication. If there's nothing written, it's multiplication. It's not addition. It's not nothing. It is multiplication. So x to the 0 times x to the 0 times x to the 0 is x to the 0 plus 0 plus 0 power times, and this becomes y to the 2 plus 2 plus 2 power. And if I clean that up a little bit there, that becomes 0 plus 0 plus 0. Now look, we know that that's 0, but I'm just going to connect it to why this 3 gets applied like this. 0 added to itself 3 times is the same thing as doing 0 times 3. And 2 adding to itself 3 times is the same thing as doing 2 times 3. And then we get x to the 0 times y to the 6th. X to the 0 is 1. And this all becomes y to the 6th. And that's your answer. Now, I did go above and beyond what I should have done for this problem, so let me first just make mention of why I did this. A couple things. First of all, I want to stress the importance of parentheses here. I want to make sure that I'm doing this whole thing raised to the power. I'm not just raising 0 to the third power. In fact, they end up multiplying. You saw this connection right here, that the 3 multiplies with the 0 because of the number of times that you are multiplying by x to the 0 power. This 2 ends up multiplying with this 3 as well because of the number of times that y squared is multiplying with itself. It does the same thing. So there's a connection there. This is not 0 to the third. This is x to the 0. All to the third. This isn't 2 to the third. This is y squared, all to the third. So these end up multiplying for that very reason. So that's something, I would have skipped these 2 steps ordinarily. Okay. The other thing is, even if I wanted to write this step, I probably would have, but I probably would not have done this x to the 0. I probably would have turned this to a 1 a long time ago. Okay, and that's what I'm going to do this second time through. So let's bring this down here. X to the 0 times y squared quantity cubed. X to the 0 times y squared quantity cubed. X to the 0 is going to become 1. 1 times y squared quantity cubed. And even better yet, look, I really should have just gotten rid of that. 1 times anything is just that thing. So this is y squared quantity cubed. So from there, look, I really should just jump from here to here. But anyway, y squared quantity cubed then becomes y to the 2 times 3 power, which is y to the 6th. It's entirely possible that a problem like this can be done completely in your head. In fact, all of these problems technically could, but as far as showing some work, it's good to know where you're coming from with it. You know, you don't want to be wrong. You want to make sure you're doing all of your steps correctly. This really would have been the way I would have done this problem, if you think about it, just kind of right here. Because like the next time I do a problem like this, I'll probably be doing it that way. Like this one right here. 2x squared divided by 5y to the 4th, all being raised to the negative 2nd power. Now, I just made mention, just like this problem here, if there's anything I can reduce or simplify inside the parentheses, I should do that first. Which means, if 2 divided by 5 could reduce, I would do that. It can't, but if this said 2 over 4, I would have reduced this to 1/2. I would have reduced it to 1/2. Now, some people start to get in this mindset of division means subtraction. No, division does not mean subtraction. Dividing something with exponents means that the exponents subtract. And again, there's a reason for that. That's different from normal division. 2 divided by 5 is not negative 3. Okay, 2 divided by 5 is not negative 3. That is not, 5. That is not how this thing works. And I only say that because, I see it very often. You take something in math that you've known forever, right? You take something in math that you've known forever, and then I don't know how this erased, and then you learn something new, and then you try and apply that new thing to an old thing that doesn't make any sense whatsoever. Makes sense with the work that you're doing. That's what I would always ask for anybody. Okay, so I have a negative 2 that's being applied to all this and all of this. Now, what I'm going to do is I'm going to apply that negative 2 to all of these. Now, remember, negative 2 does apply to the 2. It applies to every item in this product. This is 2 times x squared. So 2 gets to the negative 2, x squared gets to the negative 2. And then it's also going to apply down here. The negative 2 goes with the 5 and the y to the 4th. So if I write this out, and this is not a very exhaustive way of writing this. I will show you one other way that, I don't want to confuse you with it, but it's something else that you can do. It's likely what I would have probably done, but that's okay. So notice the importance of parentheses here again. I really want to make mention, especially with the variables that have exponents, that this 2 is not being raised to the negative 2nd power, and this 4 is not being raised to the negative 2nd power. It's the term inside that's doing that. Now, I'm not going to do anything just yet because it's a negative exponent. So let's go ahead and move items. This has a negative exponent, so it will move down here and become a positive exponent. So this will be 2 to the positive 2nd power. This is also going to move down and become a positive exponent. So now we're going to have x squared be raised to the positive 2nd power. These guys on bottom are going to move to the top. This 5 to the negative 2nd power is going to move up and become 5 squared. And then this y to the 4th raised to the negative 2nd power is going to move up top, and that's going to be y to the 4th squared. So the thing I was going to say about the other way I would have done this, and I'm going to see if I can write it up top right here. You might have noticed that everything moved. Now everything moved because the negative 2 applied to everything. This negative 2 will apply to every item in this product and in this fraction altogether. Every single item. So what's to say that's no different than just go ahead and move these things like this as long as I change that negative 2 to a positive 2. I could have written this like this first, and I could have gone right down to this step, and I'd be at the same place as I am right now. So that's up to you, right? You can do whatever you want with that. That 2 still applies to the 5, and it goes there. To the y to the 4th, it goes there. As long as that changed into a positive, everything that it's affecting will have moved places. Okay, so yeah, there's that. So now that I'm at this step here, let's go ahead and finish this. 5 squared. It's not 5 times 2. It's not like we did here, that one right here. 5 squared is 25. Now y to the 4th squared, let's see if we can do this without writing the extra step, because I want to kind of resolve this answer. This is y to the 4 times 2 power, so that's y to the 8th. All divided by 2 squared, which is 4, times x to the 2 times 2 power, which is x to the 4th. Now, with a problem like this right here, this this x squared business right here, you can't see that color. This x squared squared business gets kind of weird because you can get a 4 using the numbers 2 and 2 in 3 different ways. X to the 2 times 2 as we did, x to the 2 plus 2, or x to the 2 squared, as if the 2 was actually squared. All of these would have given you x to the 4th power. So what you can run into in some cases is what's called a false positive, meaning you could have luckily still gotten the same x to the 4th here, but if you accidentally followed the same suit, instead of doing 4 times 2 here, what if you did 4 plus 2? You would have gotten y to the 6th. That's incorrect. What if you did 4 squared? That would have been 16. You would have been incorrect there. So sometimes you'll luck out on a same answer there, and those false positives are kind of tricky when you're using the numbers 0, 1, or 2. Sometimes you run into more false positives than you know or than you actually wish to have. So let me erase that there, but this ends up being your answer. Now, I did make mention in the very beginning that if there was anything to simplify, I should have taken care of that in the first place. 2 over 5 couldn't reduce. If 2 over 5 can't reduce, whatever ends up happening in the end, like this 25 over 4, this can't reduce as well. Yeah, I can actually divide them, and 25 divided by 4 is, I think, 6.25, but I'm not going to do that. I'm just going to leave it as a fraction of 2 integers, one on top, one on bottom. So if this can't reduce, then this can't reduce. But remember when I said, what if it was 2 over 4? If it was 2 over 4, then that reduces to 1/2. Well, what if instead this said 2 over 4 squared? You can either do one of two things. You can call it 1/2 squared, which is 1 squared over 2 squared, which is 1 over 4. Or you could have taken this 2/4 squared, which is 2 squared over 4 squared, which is 4 over 16, which then becomes 1/4. So no matter which order you do this kind of problem, you should still get to the same thing. Make sure the fraction reduces one way or the other. That's why I said it's best to simplify in the beginning, for a couple reasons. The main one is you won't have to simplify again. But the other one really is that if you don't, then you're going to end up with bigger numbers. And bigger numbers to me are a lot harder to come up with how you have to simplify thereafter. 4 over 16 is harder to simplify than squaring one. I hope you know what I mean. If this said, 7 over 21, I wouldn't want to do 7 squared over 21 squared or 7 cubed over 21 cubed and then try and simplify it. 7 over 21 is 1/3. I'd rather deal with that if I could. So anyway, I exhaustively went over these ones because it's really one of the only times that I am talking about them, and I sure hope that that makes sense, that I covered this in great detail. Remember, these videos are not just for answers, they are for teaching you the stuff, so I do kind of apologize for it being long for that, but I really hope all those came into play. It looks like we covered pretty much all the properties there. We haven't talked about fraction exponents yet, but we're about to run into those. I think that I really covered all of these here. I think they all applied. Okay, let's go ahead and move on. Okay, radicals and rational exponents. Now, there's this idea behind this stuff, and I didn't write it in the properties before, but I did mention it. If you have something here raised to the m power, and you're taking the nth root of it, first of all, it is equivalent to doing this as well, and you're probably going to see me do this more often. First take the nth root of it, and then raise it to the m power. Now, all of this is a to the m over n power right here. So the root becomes the denominator of the exponent, and the power stays as the numerator in the exponent. There are reasons behind this, all that being said, if there's nothing written here, like this a right here, that means a to the first. And if there's nothing written in the root, like that means the same thing as square root. So, there's an implication right there that if nothing's written, that means there's actually a 2 that exists right there. And all square root means and cube root means and such, square root means what number times itself gives you that value. Cube root means what number times itself gives you that value. 10th root means what number to the 10th power. What number do you raise to the 10th power to get that value? Stuff like that. So I actually like to do the conversion from this way to this way because I like to talk about them in terms of roots. I know some people don't. But what I want to make sure that you understand is this is not, so this first one, 512 to the 1/3 power, it's not the same thing as doing 1/3 of 512. This is not 512 times 1/3, which is some answer. No, not at all. because 512, actually here, let's come up with what that number is. Gosh, I'm not sure what it is. But anyway, let's say that number was about 140, which it's not, but let's say it was like 140. If it was 140, then that would mean that 140 times 140 times 140 is 512, and that's certainly not true. 140 plus 140 plus 140 in that case would be 512, because that's what you're doing when you're taking a third of something. But no, we're raising it to the 1/3 power, so we're trying to say what number times itself is 512. So when I do this, I'm going to write this as cube root of 512. And again, that's just a transformation that for me, I like. Maybe it didn't help me find the answer yet. In fact, off the top of my head, I'm trying to think what the answer is. Okay, yeah, I think I know what it is. So here's how you can test this. And here's, I'm not going to use the calculator in this part here. There's a number that I multiply by itself 3 times to get 512. Now, you can start to do some tests. Hey, is 2 times 2 times 2 it? I mean, eventually you might tell yourself some of these numbers are too small. So that's 27. And then, but you're not sure because some of them get kind of large kind of fast. 4 times 4 times 4 is 64. You can see it's already 8 times larger than 2 times 2 times 2. And I'll stop at this one before I start to kind of reveal what it is. But at some point, you keep working there. Now, one thing I want you to see here is that when I'm multiplying numbers by themselves, take a look at the evens. An even times an even is an even, and an odd times an odd is an odd. So one thing I do know, if I'm going to list out some of my numbers, 2, 3, 4, 5, 6, 7, 8, 9, 10, notice how I didn't do 1, first of all, because 1 times 1 times 1 is just 1. I know that my odd numbers will be gone here because I know that it can't possibly be one of those. Now, here's some other fun fact stuff for you. I do know, I do know what the number is already. Now, not because I already did 2 times 2 times 2 and 4 times 4 times 4, but I already know what the number is because of this. 10 times 10 times 10, say you want to go very extreme. You're like, hey, let's test this first. 10 times 10 times 10 is 1,000. It's a 1 followed by 3 zeros. Hopefully you know your powers of 10 and how that works. This number's too large for 512, so I know it's not that. And it's not 9 because the odd number stuff. Now, going back to 2 and 4, along with 6 and 8 here, check this out. Right here, cubic numbers have a very interesting thing in their ones digit. When I cube 2, actually, you know what? I'm going to write all these out so I can prove it to you. Because this is kind of another way that you can test this thing. When I cube 1, I get 1. When I cube 2, I get 8. When I cube 3, I do 3 times 3 is 9. 9 times 3 is 27. It's going to end in a 7. This is not what 3 cubed is, but it ends in a 7. 4 cubed, 4 times 4 is 16. That 6, that last number times 4 ends in a 4, 24. So this ends in a 4. 5 times 5 is 25. 25 ends in a 5. 5 times that number ends in a 5. 6 times 6 is 36. That number ends in a 6 as well. 6 times 6 also ends in a 6. 7 times 7 is 49. That number ends in a 9. 7 times 9 is 63, so that ends in a 3. 8 times 8 is 64. That number ends in a 4. 8 times 4 ends in a 2. That's 32. 9 times 9 is 81. That ends in a 1. 9 times 1 ends in a 9. And 10 times 10 ends in 0. 10 times 0 ends in a 0. All of these numbers end in a different ones digit. 1 cubed, 2 cubed, 3 cubed, all these end in a different ones digit than the others. Now, is this true for everything if you square them and if you raise them to the 4th power? No. But you could play process of elimination this way as well. I already knew that the odds won't work because they end in odd numbers, because they are odd numbers. So I know those won't work. And I knew this number was too large. You should know this number is too small. So in the end, it comes to, am I cubing a 4, a 6, or an 8? Well, this number is 512. And 8 ends in 2. When you cube an 8, it ends in 2. If you raise to the 4th power, it ends in a 6 because 2 times 8 is 16, stuff like that. But this one ends in a 2. It can't be any of the others. Just for good measure, 6 cubed is 216, and 8 cubed is 512. And you know what? I want to note one more thing actually with this because I didn't really make mention of it. Unless you're using a calculator and you're being asked to round, you're not going to be given numbers that don't have a perfect cube. It's not like we're going to give you the cube root of 513 and ask you to compute it and have you guess, oh, that must be 7 cubed because 7 ends in a 3. No, they're not going to give you this because that's just not going to show up. We're going to give you numbers with these kinds of problems, or at least these kinds of problems are going to give you numbers here that do that kind of thing. So, in terms of erasing everything, the answer is 8. Now, did I go above and beyond what I should have done for that problem? Maybe. You know, a part of it is really testing. You know, when I first saw this, I was like, I don't really know what the cube root of this number is. There are ways of figuring out. There are some numbers you should know what are cubed. I for sure know them up to 6 cubed. 7 cubed I think I do know as well. But, you know, this one I don't always know. I sometimes have to do multiplication to figure it out. But, you know, it's a matter of testing. It is. But understand that we are not dividing this number by 3. We are not dividing this number by 3. We're saying that 8 times 8 times 8 is 512, which is true. Okay, this problem seems a lot easier. The cube root of 8. Well, it's 2. It's 2 times 2 times 2. And I'm not going to say much more about that problem right there. That's it. All right, the 5th root of negative 243. All right, well, now we're cooking. Okay. First of all, I want to write you the transformation equivalent of this as a rational exponent because I want you to see it loud and clear. It's like that. Negative 243 to the 1/5 power. Now, I'm not going to use this. This doesn't really help me. But notice what I did. I used parentheses around the negative 243. Just so you know, for this particular problem, if I didn't write parentheses, I would still actually get the same answer. But that's one of those false positives, luck of the draw. You don't want to run into something like that and be wrong the next time you try one. I'll show you something in the calculator when we get to this problem, for example. But that is the equivalent of this. This is grouped to the 1/5 power because it is inside the root right here. Okay, so anyway, trying to find the 5th root of this thing. You notice what I talked about with this being an odd number. Not with what it ends in, but with it being an odd number. I'm only going to test odd values. Okay. Now, I happen to know what the answer is here. One thing, let me erase what's kind of on top right here, all this stuff. One thing for sure is I know that it's not 5 because 5 times 5 times 5 times 5 times 5. I do know that those always end in a 5. I don't know what the answer is off the top of my head right now, but I do know that it ends in a 5, so I know that can't be it. So, you know, you might as well go from smallest to largest. Obviously, 1 times 1 times 1 times 1 times 1 is just 1. So let's try 3 times 3 times 3 times 3 times 3 to start. By the way, actually, I didn't make mention of this. These should technically all be negative. I'm just talking about the value itself first. So negative 3 times negative 3 is 9. 9 times negative 3 is negative 27. 27 times negative 3 is positive 81. And 81 times negative 3. See, 8 times 3 is 24, so it seems like that's really popping right into what we need there, negative 243. So that one ends up being it. See, you try 5 times 5 times, I think you get a number in the thousands, and you already know that you've overshot your value. So, you know, sometimes there just aren't so many answers to choose. You know, like when I talk about, you know, get familiar with these, you know, that's exactly what I mean. You know, make it familiarization. I know what this number is because I've seen it a lot before. There's kind of a difference. And I also know what 3 to the 4th power is. I know that that's 81, so that helps me. Now, this becomes a negative number, and I know some people think that you can't be taking the root of negative values. That's actually not necessarily true. First of all, you can take the root of any value, positive or negative, but you can't take the square root or something of a negative number and make it be a real number. There's a difference between the two, and we're going to talk about it here. The other thing is that if you do it to an odd root, that means there's an odd number of values being multiplied, and all of them are negative. When you multiply an odd set of negative numbers together, the result becomes negative. See, a negative times a negative becomes a positive, but a positive times a negative becomes a negative. So check this out. We start with a negative, times a negative is a positive, times a negative is a negative, times a negative is a positive, times a negative is a negative. As long as there's an odd number of negatives being multiplied, you will get a negative result here. By the way, I don't know why I boxed this as my answer. My answer is negative 3. There you go, like that. So anyway, yeah, it's, you know, that's kind of how you approach that problem there. 625 to the 3/4 power. Okay, this is where I get to play with this transformation idea and do this. Now I'm going to first start by writing it this way right here. I'm going to write 625 cubed and all to the fourth, or the fourth root. Fourth root of 625 cubed. What this would mean is I would take 625, I would multiply it by itself 3 times, and then I'd take the fourth root of that number. Now, you might already be, you might already be like, I don't want to do that. Guess what? Neither do I. So you know what? I'm not going to. There's a reason why I also wrote this approach right here. I would rather go small first and go big after, especially because I don't like multiplying big numbers by themselves, and I especially don't like trying to figure out what the fourth root of that number is. It's just not that familiar to me. I don't like doing that. So instead what I'm going to do is I'm going to do the same thing, only I'm going to take the fourth root of 625 first. Then I'm going to go ahead and raise that to the 3rd power. Because this is a number I might be able to find the fourth root of very easily, and then it will give me a small enough number that I really wouldn't mind cubing. Now, I'm trying to think of something on the top of my head right here and trying to decide, is there any number that ends in a 5 besides 5, that gets raised to powers? Does 3 to the 4th power give you that? Does 7 to the 4th? Does 9 to the 4th? I don't think so. I think the only ones that actually end in a 5 are the ones that end in a 5. So the only possible scenario is if we're talking about 5 times 5 times 5 times 5, or something like 15 times 15 times 15 times 15. Now, you'll probably know that it can't be the bottom one because 10 times 10 times 10 times 10 is 10,000. So it's already way above this. I think this is the only one that can actually hold. Now, I already know that this is the answer. 5 times 5 is 25. 5 times 5 is 25. 25 times 25 is 625. It's one of those squares that you may or may not know. So the fourth root of 625 is actually just 5. So what's going to happen is this turns into 5. And then I'm going to go ahead and cube all of that 5 right there. So 5 times 5 times 5. 5 times 5 is 25. And don't let this one be too hard for you. You should know 25 because you should know quarters. 5 quarters is $1.25. So this becomes 125 right there. Or 4 25s is 100, 4 quarters is $1, something like that. Or, like I said, maybe you'll just familiarly know that. But anyway, so that's the answer there. And again, I didn't really use the calculator for that, but there you go. Last one, negative 25 to the 1/2 power. Okay, so this has a couple things to make mention of. First of all, if I do a transformation from this to something like this or whatever, that's fine. That would be, notice how this is in parentheses. That means the negative goes inside the root, inside the radical with the 25. Negative 25. Now, I could write something like a 2 right here and a 1 right here. But you should already know at this point that you've explored exponentiation is that anything to the first power is just that thing, so this 1 can technically go away. And probably just for good practice, when they write square root, they tend to not write this 2. So that can technically go away as well. And now the parentheses aren't needed, so we're really just looking at the square root of negative 25. Now you're asking what number times itself is negative 25. And I know that a lot of people would want to say negative 5, but the problem is negative 5 times negative 5 is a positive 25. So it can't be negative 5 for that reason. And obviously 5 times 5 is 25 as well. And you can't do 5 times negative 5 because those are two different numbers. So you can't do that. So what's the answer? Well, the thing is, there is no, it's called no real solution. I did make mention that it is possible. It is possible to take the square root of negative 25, but it won't be a real number. And yeah, there are things, they're called imaginary numbers. There is such a thing, it does exist. We're not referring to it. We'll just go ahead and say no real solution here. Now, how can I kind of make more mention of that? I'm going to go ahead and bring up this calculator right here, and I'm going to go ahead and do the square root of negative 25. And you're going to get a non-real answer, error, non-real answer. There's a domain issue there. So quit out that. Now, what if you went to the original problem? What if you weren't doing any transformations and you said, okay, I want to do negative 25 to the 1/2 power. So I do negative 25, I hit my raise button right here, and I do 1/2. there are going to be a lot of issues with the answer that I'm going to get right here. And I'll tell you what answer I'm going to get. It's not going to be no real answer. It's going to be negative 12.5. Now, something weird happened there. And this is where, it's good to double check, but if you're taking a test where you can't do it, then, that's one thing. There are two issues. Number one, I didn't use parentheses. This problem used parentheses. I should use parentheses with it. There's a big difference between using parentheses and not, and I almost didn't use them again, between using parentheses and not, because the parentheses say that the negative also is being raised to this power. If I don't have the parentheses in here, then it becomes an issue. So to the 1/2 power again. Now, guess what? I'm still going to get negative 12.5. Okay, what's going on? Order of operations here as well. I'm raising negative 25 to the first power. What's negative 25 to the first power? That's negative 25. Then I'm dividing negative 25 by 2. This 1/2 is not all written in the exponent like this. I have to get this in parentheses right here. That to the 1/2 power. The 1/2 needs to be in parentheses as well. 1 divided by 2. Like that. Now I get my non-real answer. And that, that should match. That's the same thing as the square root of negative 25. Now, let's say I didn't use parentheses around the negative 25 and I raised it properly to the 1/2 power like this. This is not going to give me the correct answer. So there's a difference. This is going to give me negative 5. So there's a difference. There's a difference between getting negative 25 all raised to the 1/2 power and the opposite of 25 to the 1/2 power. By that, I mean writing it like this. These are not the same thing. Parentheses make the difference in everything here, because this one, what this one does is it takes 25 to the 1/2 power, which is 5. And then it takes the opposite of that. This guy is negative 5. That does have an answer. This one does not. That's why I said for this problem right here, when I was writing out that negative 243 to the 1/5 power, okay, when I wrote that thing out, I wrote it in parentheses, and I said, you know what? If you wrote it without parentheses, you'd still get the same answer. This is one of those false positives. The reason is because negative 243, the 5th root of negative 243 has a value, negative 3, because of its odd root. Because of its odd root right there. This one, the 5th root of 243 is 3, and then take the opposite of it, you get the same answer. So both of these end up being the same thing. You shouldn't assume them to be true, though. That's why you always practice things with parentheses when you're supposed to. So those aren't the same thing right here, even though these are. But I wouldn't expect them to always be the same thing. So if something's grouped, like this on the inside, be very, very careful how it's written. Likewise, if I want to write this one into its root notation, I would leave the negative on the outside. Negative square root of 25. This is negative 5. This is negative 5. Because square root of 25 has a value of 5, and then you take the opposite of it. The one we're looking at, though, is no real solution, and that would be the answer to that one. One more thing in the calculator, and what I'm using right here is a graphing calculator, and I know it doesn't look like yours if you have a scientific one, but also you might be using a scientific one, and you might not be getting this little number right here, and you might not have to use parentheses here. That's because you're using a mode called MathPrint. If I go to mode right here, and I take that back, mine doesn't actually have it. The TI-84 does. But if you go to mode, you can change something to what's called MathPrint mode. And when you hit that raise button, that's not going to show up. Instead, it's just going to make the little small part, and you can just type 1/2 and you'll be fine. But you got to know how parentheses and order of operations work anyway. A lot of people say that their calculator's, doing something wrong and it's messing up. It's actually user input. All your calculator knows is order of operations, and it knows how to calculate things correctly. So your calculator is never going to give you an error. You'll never be able to type 2 + 2 and have it glitch out and give you 5. Know what I mean? Anyway, that's section 6.2, radicals and rational exponents. Moving on. 6.3, exponential functions. We're going to graph two functions, and then we're going to find the equation of a function right here. Okay, but neither of these have any sort of shifts. We're not going to be having anything else up top or anything on the side. This will be nice and dandy right here. I will start off with a table, but understand that I'm going to show you a tableless method of graphing these as well. I believe that both are equally important to do. The table is nice to draw a connection, and it helps when we start talking about geometric sequences. What I'm going to do is I'm going to substitute some values here, 1, 2, and 3, more than 0, -1, -2, -3, right here. Now I'm going to start with 1, 2, and 3 here. First of all, this is 9 times 3. You don't change this to 27 because order of operations. I have to do 3 to the power first, and then I multiply it by 9. And 3 to a power might change my value of 3. See, when I get to 3 squared right here, 3 squared times 9 is not the same thing as 27 squared. So nice big difference there. So it's not that. So I have to leave it like this. Let's go ahead and extend this table. I'll show some work on the inside. So here, we're going to get work on the inside. We'll get y values. And when I get my x, y values, I'm going to plot them on the graph, at least the ones that I can fit. So 9 times 3 to the x. So let's start with 1. Let's do 9 times 3 to the first power. 3 to the first power is 3. 3 times 9 is 27. Already, 1 comma 27 looks like a point that I can't fit on my graph. There's a point at 1 all the way up to 27. But I might change my scale. We'll see. And obviously, these ones probably won't fit either, so this is maybe not the best idea. But anyway, 2. We'll do 9 times 3 squared. 3 squared is 9. 9 times 9 is 81. And obviously, 2 comma 81 doesn't really fit, but that's neither here nor there. I'm doing this for pattern recognition only. 9 times 3 cubed. 3 cubed is 27. 27 times 9, oh, that's, let's see, I should have 243. 243. Obviously, that can't fit either. Okay, we start to draw those up, and hopefully you start to see a pattern here. X is going to increase by 1 each time right here. And every time x increases by 1, y is not increasing by a common difference. I'm not adding something from one to the other, but I'm tripling my previous value. 27 times 3 is 81. 81 times 3 is 243. Now that should make sense because that follows the idea of exponentiation. The only thing that changed from this one to this one to this one is the exponent. The exponent increased by 1. And what is exponentiation? It's the number of times something multiplies by itself. Here, this becomes 9 times 3. This is 9 times 3 times 3. This is 9 times 3 times 3 times 3. What's 9 to the 4th? It's going to be one more multiple of 3 than this one. So you're just multiplying by 3 one more time than you did before, and that's really all it is. So I don't want to, and I'm not going to here, I don't want to substitute this every single time and try and compute it. I would have had an easier time doing 81 times 3 than 9 times 27. That's just me. Personally, it's easier for me. Now that's going as x increases by 1. Well, every time x decreases by 1, then you're multiplying by 3 one less time than you did before. So when I go backwards, that would be equivalent to saying dividing by 3 and dividing by 3 and so on and so forth. So whether I want to do this way, 9 times 3 to the 0 power, 3 to the 0 power is 1 and 9 times 1 is 9. This should make sense here because now I have 27 divided by 3 is 9. Okay, so that seems like it seems like that's still connecting there. And then this one right here, here's where it's really nice to not have to use this. 9 times 3 to the negative first power, and this is where people can get negative answers like negative 3 as an answer or negative 27 or something random like that. Remember, negative exponents don't mean negative numbers. It means how many times you're dividing by 3 now. So notice it's kind of like taking 9 and doing over 3. 9 over 3 becomes 3. And this keeps dividing this way. Let's divide by 3 again, and that's 1. And let's divide by 3 again. Let's not use the calculator. 1 divided by 3 is 1/3. Now I feel like kind of extending this table this way in negative territory. I think these are going to be easier numbers to graph because I want to include some fractions and really get the understanding of, okay, well, that's what fractions are. That's how we're using them, and feel comfortable with it. So I'm going to move all this up. Sorry about that. And I'm going to include 2 more, negative 4 and negative 5. Negative 4, negative 5. Notice I'm not really using the inner table anymore. That's going to be way too tough for me to do. I'd rather keep dividing by 3. Now, here's where stuff gets weird though. We got to take 1/3 and divide it by 3. 1/3 divided by 3 is not 1 over 3 divided by 3. It's 1 over 3 times 3. It's not 1 over 1. It's 1 over 9. If you don't know that, don't write divided by 3 here. Do something else. Write times 1/3. Dividing by 3 is the same as multiplying by 1/3. You multiply by 3's reciprocal. 1/3 times 1/3, 3 times 3 is 9. That's what happens on bottom. Last one times 1/3 again. you get 1 over 9 times 3, which is 1 over 27. So you see a bunch of points right there, and the ones that I'll be able to graph look like probably these ones right here. It's kind of unfortunate that I get no positive ones, but I can always pretend like I'm extending this table. I'll shoot it up anyway. But anyway, those are the points that I'm going to graph right there. So if I try and do those, I have 0, 9, negative 1, 3, negative 2, 1. All right, here's where stuff gets a little weird. Negative 3, 1/3, so a little less than a half. Let's say about right there. Negative 4, 1/9, getting pretty close to 0 at that point. And negative 5, 1 over 27. It almost might as well be 0, but it's not quite. I'm doing the best I can with that. Now that I have my points, I'm going to erase my table so I can really draw the graph and play with this a little more. So I got rid of that right there. And this, I can never do smooth curves on a computer, so sorry if this ends up not being smooth as well. But here's what's going to happen as you keep taking a third of your previous value as I go to the left. First of all, as I go to the right, this will never go straight up. It'll keep increasing because I can keep plugging in a value to x. 3 to the 10th power is a number, so when x is 10, y is some value that's way up there. I mean way, way, way up there that I can't even see. So as I keep increasing x by 1, I'm going to keep going higher and higher to infinity and beyond. But as I keep decreasing x by 1 over here, what's happening? I had 1 over 27. I'm going to take a third of that. That's 1 over 81. Take a third of that. 1 over 243. Take a third of that. 1 over 729. That, 1 over 729, what is 1 over 729? I mean, geez, you're getting a really small number there. 1 divided by 729, oh man, 0.0013. What's 1 divided by that number? 729 times 3. Notice how I use parentheses here. I don't actually know what this is. Okay, now that's not 4 point something. That is, this means I have to shift this decimal place 4 over. So 0.0004 something something. Anyway, incredibly small. As I keep taking a third of something, I'm getting closer and closer to 0. Now I never can actually get 0. No matter how many times you divide by 3, you never actually get 0. And furthermore, I need to really stress this, you never actually become negative, right? So we'll never get negative numbers as a result, but we'll never get 0. So what I'm going to do is make this kind of green dotted line right here. This is called an asymptote. An asymptote is kind of this nice little pretty threshold that says as I start to decrease x forever, in this case, I start to get closer and closer to this line, but I never actually touch it. Now, did I draw it and did it actually cross? Yeah, I might have. That's just a mistake. But it just gets closer and closer and never touches it. It's a nice feature on all exponential functions. Every single exponential function you do will have this asymptote right here. Every single one. There is none that will not. Okay. Now, depending on which way they go is one thing. And in fact, this is the only problem I'm going to do a table with. I'm not going to do a table here. So I need to start explaining how to do this without a table. Okay, first of all, these two numbers have meaning in the graph. The 9 has meaning in the graph, and the 3 has meaning to the graph. And actually, when I write this as an equation, this is y equals a times b to the x power. And that's what we're looking at. We're looking at a scalar multiple right here, and then a growth factor right here. 3 is the growth factor, 9 is the scalar multiple. Okay, I didn't start with 0 in the table, but if I did, 3 to the 0 power is 1, and 9 times 1 was 9. You can see that this 9, I should probably keep these the same color. You can see that this 9 shows up right here. Now, this 9 will kind of always show up right here, assuming no shifts, and we are not doing any shifts here. This 9 occurs when x equaled 0. Now, why is that so? Well, what if we go up here and we did y equals a times b to the 0 power? Anything to the 0 power, assuming b is a positive or is a non-zero number, b to the 0 power is 1, so that's a times 1, which is a. So there's this nice idea with these graphs that we do. Anytime that you have an exponential function, and I'll draw the kind of 4 different functions that you'll see, but say it went this way. Anytime you draw an exponential function, the y-intercept occurs at 0, a. So this number is where I place my y-intercept. So, I'm not going to start this problem yet officially, but this number is a -4. Guess where I'm going to start? At 0, -4. that will be my starting point. It's just a nice little way of saying this number actually has meaning. And you'd use pattern recognition to figure that out, but this also shows you that exact same thing. If I raise something to 0 power, it just becomes 1. And anything times 1 is itself back out. So 0, that means x equals 0. And x equals 0 is in reference to the y-intercept, and that's what we get. Now the next part, this 3. How did this 3 apply? Well, you saw it in the table, the one that I already deleted, that every time I increased x by 1, I multiplied by 3. So when x increased by 1, I did 9 times 3, that's 27. X increased by 1, I did 27 times 3, which is 81. I do it again, I multiply by 3 again. And that's actually true. So if I had another point way up here on the graph, that would have been 1, comma, 9 times 3, which is 27. So I don't need to use the table. You can use it, but don't use it for the reason that you're plugging in values for x. Do it for the reason that you are recursively, and that word's going to pop up again later, recursively changing y from one value to the next using a common growth pattern right here, this common multiplier of 3. Now that's every time x increased by 1. Every time x decreases by 1, it looks like I divided by 3. 0, 9, then divide by 3. That's negative 1, 3. Divide by 3, that was negative 2, 1, divide by 3, that was negative 3, 1/3, etc. So that just keeps going in that direction the same kind of way. I keep dividing by 3. So when I do this next problem, I'm actually not going to be using a table at all. Now the one caveat with this is that I'm technically not multiplying the y value by 3. Yes, the y value times 3 gave me that. Technically what I'm doing is I am increasing my distance from the asymptote. So my distance from the asymptote right here is 9, and I multiply that by 3, and then my distance from the asymptote is 27. The reason why I say all that is because what if this was a shifted graph? What if this graph was shifted up here instead? Well, this point wouldn't be 0, 9 anymore. Obviously, this is a different equation, but this point wouldn't be 0, 9. This point would be 0, like 12. But when I multiply by 3, I'm going to be 27 away from the asymptote still. So I'll be at 1, 30. I won't be at 1, 36. I'm not going to multiply this by 3. I'm going to multiply this distance by 3. But if you're in Algebra 1 and if you're not doing asymptotic shifts, then I wouldn't really worry about that anyway. You can feel free, go ahead and multiply that by 3. Let your next teacher refer to table as graphing for you. I'm sure they'd be more than willing to help if they in fact catch on that pattern, because that makes it a lot faster. I mean, a lot faster. Furthermore, it helps me. It helps understand your idea of exponentiation. I say this in my class all the time. Any untrained monkey, not untrained, any trained monkey can substitute x values into here, compute it, calculator or not, and plug them in as points. What we want to do is expand our understanding of exponentiation, and I'm going to do it even further on this problem here. Get that same understanding of this y equals ab to the x. Okay, there is no number here, but this problem right here, y equals negative 4 times 1/4 the x power. Now I said we're going to start at negative 4. It's the same reason why we started at 9 over here. When this is 0, raised to the 0 power, we get negative 4 times 1, negative 4. So when x is 0, y is negative 4. That is my y-intercept. That's where I'm going to start. Now here's a 1/4. There are a couple ways you can talk about this 1/4, but as x increases by 1, every time x increases by 1, you multiply by 1/4 one more time than you did the previous time. So negative 4 times 1/4, you could also say negative 4 divided by 4. That's going to be negative 1. That's where my next y value is going to be. 1 away from the asymptote, 1 underneath the asymptote right there. Negative 1 times 1/4 is negative 1/4. Negative 1/4 times 1/4 is negative 1/16. Already too small to kind of keep going there. If I went the other way, I would be doing negative 4 divided by 1/4. And how do you write negative 4 divided by 1/4 and not make it sound really weird? You multiply by its reciprocal. 1/4 is 4 over 1. So negative 4 times 4 is negative 16. So if it fit, I'll make it fit. I'll put it like down here. Maybe that's 16. Negative 16. It's way down there. And I would draw my curve again because every point gets applied here. And I cannot, for the life of me, do these very well on a computer. Sorry about that. But this also, it never actually reaches 0. It gets closer and closer, never actually becomes it. So I can do another asymptote right here at y equals 0. That's the x-axis. Is this a required part of the graph? No. It's nice to draw. This is your graph. That's required to draw and required to connect the dots. This dotted line kind of says I'm not going to cross it. In fact, you might have seen me do this with the previous problem as well. Notice how I always draw arrows because these go on forever to the right and left, to the right and left. This one goes forever down, but it goes up only until it gets closer and closer to 0, never actually reaches it. So I'll just say up until 0. This goes up forever and down until 0. But it does go forever left, and this one does go forever right. So I did draw an arrow, but notice how I drew a half arrow. Something I picked up when I was in high school and I was doing, I think, problems like this. And, arrows say it goes on forever. Half arrow will also say it goes on forever, but for me it kind of says it doesn't always keep increasing. Technically it does because it's getting closer to 0, but it never crosses 0, So it keeps going, but it does converge. It never actually truly, becomes that. So anyway, understand, one more time, I started from this number because of that. And then I took a fourth of the previous number here. Okay. Now, I'm kind of done with these two problems, but one more thing I'm going to make mention of, and I'm going to do it down here, is that I should know the behavior of this graph based on what my A value is and what my B value is. Okay. So I'm going to draw 4 little graphs here because exponential functions can do one of 4 things. Let's assume there are no shifts, so your asymptote is at y equals 0. You can either start from the asymptote and start increasing like that. Start from high up and converge at the asymptote. Start from decreasing form and converge at the asymptote up there. Or start from the asymptote and start decreasing downward. Okay, these 4 different things. This occurs when you have a positive A value and a B value greater than 1. And the B values be greater than 1 because if I multiply by a number bigger than 1, then it will become larger. Here, I will also be a positive A value because of the y-intercept. You can think about it that way. But here, I'm going to get a B value that's a fraction. It's a positive fraction between 0 and 1. But say like 1/4 or 1/2 or whatever. Take half of what you were before. Take a quarter of what you were before. 92% of what you were before. You're going to see that as well. That's where it starts, it shrinks. This is called decay. It's called positive exponential decay, but it's decay nonetheless because it's lessening what it was before. It's getting closer to the asymptote in that sense. This is growth, positive exponential growth. This one's a lot like this problem right here. I had a negative A value, but a B value between 0 and 1. Because here I started at something largely negative, and I shrunk the negative value. I got closer to 0. -1, -1/4, -1/16. I am decaying in the negative direction. This is still called decay. It's negative exponential decay. That should say decay. And this one right here, it's a negative A value, and pretend like it was multiplying by 4. Well, I'm increasing in the negative direction. So I'll have a B value that's greater than 1. -4 times 4 is -16, times 4 is -64, etc. It keeps growing. So this is negative exponential growth. So I should know what my graph should look like just by looking at the equation. I might not be able to graph it perfectly yet, but I should know what to expect for my graph if I do one of those. That's just a nice little expectation thing. Pause that, rewind that, and pause that, and you take a look. Okay, write an exponential function f represented by the table, x and y. Now function f, they're referring to the same thing you saw up here, f of x. I even said y for these because y and f of x are both the same thing. So f of x equals. So what we're going to do is come up with an exponential function that looks like this. A times b to the x power. Okay, a times b to the x power. And, and we need to discover what a and b are. Well, notice how I made mention of how how all this kind of stuff works here. I get my a value when x equals 0. Remember, if I take f of 0, I will get a times b to the 0 power, which is a times 1, which is a. F of 0 equals a, meaning when x is 0, I will get my y equals a value. This, too, right here, is my a value. This is the value of y when x equals 0. It starts right there. Now, the table, it doesn't matter what the table's doing. It doesn't even matter if 0 is written here. You'd have to find 0 if it's not. What if it was cut off? What if this wasn't here and it was cut off right there? I would have to find a in a different way. I'd have to decrease x by 1 and do something over here. But this one shows the a value. Now the b value is all about every time x increases by 1, what y is doing. X is increasing by 1, plus 1, plus 1. And what is y doing? As I go from 2 to 1, as I go from 1 to 0.5, and this to this one as well. Now one thing I'm going to do here, I'm going to change this to 1/2 and 1/4, because I know that that's what they are. And, you know, aside from one section, which I think is the next section, I'm really going to avoid using decimals if at all possible. I'd like to talk about fractions and do it. Now you might say that we're dividing by 2, and that's all good and dandy because that's true. That's not false. You are dividing by 2 each time, but that is not your b value. That does not mean that b equals 2. b does not equal 2, because it's about what are you multiplying by, not what are you dividing by. What are you multiplying by? Well, dividing by 2 is the same thing as multiplying by 1/2. So when I go from 2 to 1, yeah, I divide by 2, but I'm also multiplying by 1/2. Times 1/2, times 1/2, times 1/2. Your b value is 1/2. That's what we're multiplying by. Remember what this equation looks like. A times b to the x, not a divided by b to the x. So your equation here, if a is 2 and b is 1/2, you'll get y equals 2 times 1/2 to the x power. Now you have to use parentheses specifically for a fraction. If it was a negative number, you'd have to as well. If it was an integer, you don't have to, but then you also have to write it times right there, because like if it's like 2 times 4 to the x power, I can't write that. I have to do 2 times 4 to the x power. Might as well just use parentheses. You'll see that parentheses were used for both of these problems right here. This one and that one. So good practice, use parentheses there. That doesn't make you raise it to the x power first. That just makes sure you know that this is multiplication, and that makes sure that everything inside here gets raised to the x power. See, I can't write this. I can't write 2 times 1/2 to the x power, because this doesn't show what x is being raised with. It looks like here x is only being raised to the first power. 1 is being raised to the x power. 2 is not being raised to the x power unless I wrap it around parentheses. Same thing with a negative number. What if it was 2 times -2 to the x power? Well, you got to be careful, because this just gives you 2 to the x power and then makes it negative. You have to make sure you do -2 to the x power. Now, you're not going to be drawing any graphs with a negative b value, or a b value of 1, or a b value of 0. We'll be getting b values between 0 and 1, or b values that are greater than 1 when we graph. When we run to geometric sequences, you might look at some negative b values, though. Okay, there's the answer to that, and that's 6-3. Okay, exponential growth and decay. There are going to be a couple of problems here. First, we're going to refer to these. Not going to take too long in these ones, but then we're going to have some word problems. Rewrite the function to determine whether it represents exponential growth function, an exponential decay function, it should say an exponential growth function, an exponential decay function, or neither, and please explain. Sounds good. Okay. Going back to our previous example that we saw, you saw there was multiplying by something, and you saw this ended up being a 1/2. I told you that b value between 0 and 1 is decay, just like this is decay as well. What happens with the decay, what happens with the b value less than 1 right here is you do run into what's called exponential decay, because you're looking at a b value that is less than 1. It's between 0 and 1. When I multiply 10 by 0.65, it kind of doesn't matter what's up here, as long as this isn't like -2/8. It doesn't really matter what's up here. The fact of the matter is you're still going to be raising it to a power, which means at some point you'll be multiplying by 0.65 as t increases. So as x goes this way, y is going to end up going that way, because multiplying by 0.65 is, all I have to put is that this is less than 1. This is less than 1. It's it's between 0 and 1. We'll put that. This represents decay. There's a b value between 0 and 1, and every time you multiply by a number less than 1, you become a smaller version. What else might be helpful is for the next part that we do here. This is equivalent to writing 10 times 1 minus 0.35 to the t/8 power. You're going to see a reason for this here, but this means a 35% decrease of your previous value. When we're taking 65% of something, you're taking a 35% decrease of it. 1 minus 0.35 is 0.65. Okay, f of t equals 4 times 1.25 to the t plus 3 power. Here we go. Well, that's also equivalent to 4 times 1 plus 0.25 to the t plus 3 power. So you can either put it this way. This is a 25% increase. That does represent growth. Now, it's an increase, whereas the other one wasn't a decrease because I'm adding 0.25 to 1 as opposed to subtracting 0.25 from 1. But I could also just say 1.25 is greater than 1. That's, to be honest, it's good enough reasoning. You're multiplying by something raised to a kind of, positive-esque representation of an exponent, even though we don't really look at these too much. We'll look at something like this, like this. But that's, for these 4 problems, that exponent's not going to matter too much, except for the fact that the exponent's a variable. And that's going to determine everything here. Okay, next one, y equals 1.06 times 8t. Again, that's 1 plus 0.06 to the 8t power. As we're adding, that does mean a 6% increase. And of course, that does mean growth. And of course, 1.06 is also greater than 1. So, I mean, there's not, oh, hang on, I didn't write growth here. Growth and decay. These problems don't really get much more difficult than that when it comes to it. This number is less than 1. It's between 0 and 1. So this is decay. You take 84% of your value, you are less than 100%, right? It's 16% off. 100 minus 16 is 84. So it's 16% decrease. Decay, growth, growth, decay. Okay? All right. All right, some more on this stuff here. Actually, this is still before the word problems. Determine whether the table represents an exponential growth function, exponential decay function, or neither, and explain. All right, well, you have some options here, and I'm going to play with these options a little bit because I'm going to help you create more equations out of these as well. But all we're trying to see is how y is changing. Now, what I've seen on tests before is people say, hey, 3, 6, 12, 24, the numbers are going up, so it's growth. You're not wrong. It is growth. It is growth. But if this said 3, 6, 9, 12, that's also growth. But this, 3, 6, 9, 12, is called linear growth. That's called linear growth because you are increasing y by 3. You're just adding. That's linearity. Plus 3, plus 3, plus 3. So it's not enough to just say if it's growth because if this was the table, that's not exponential growth. So I would call that neither. It's not decay either. I would say neither. It's linear growth. But you don't have that. You have this right here. So what we're going to do is figure out if we're multiplying by a number over and over to get this. Now, you might recognize, yeah, that's times 2 and times 2 and times 2. Yes, you are doubling your output. You're doing double what you did before. Let's say you didn't know what you were multiplying by. Let's say you had trouble with it. What you can do is take one number like 6, divide it by the number before, 3, and figure out what that is, and see if you get the same thing here. Take this number 12, divide it by the number 6, and you get that. Take this number 24, divide it by 12, or by 12, and you get 2 again. So this commonly is growing. It's not growing by 2. It's growing by a factor of 2, by a multiple of 2, by 200%, or by 100%. It is doubling what it was before. So this is, yes, this is exponential growth. Not because the y values are increasing. It's because they're increasing by a common factor of 2. Increasing. Y is increasing by common factor of 2. Now let's say you wanted to get an equation out of this. All right. Well, 2 represents the b value, and a is the y-intercept as it was before. So when x is 0, a is 3, or y is 3. So a is 3. So your equation, as far as y equals a times b to the x, this equation can get us to figure out any of the ones that we want after that. Start with 3 when x is 0, and every time x increases by 1, you double your output. If you wanted to write it with that exponential stuff we did, the growth model stuff we did before, that's 1 plus 1. The reason why I say that is because this means a 100% increase. You are doing a 100% increase, you are doubling your amount. Kind of sweet. Anyway, that's totally growth. Totally exponential growth. for this reason. Y increasing by common factor of 2. Okay, next one. These y values are going down. Now, that doesn't necessarily mean it's an exponential decay. For it to be an exponential decay, you have to do the same thing as before. You have to know that there's a common factor. You're multiplying by the same thing over and over. You could say dividing by the same thing over and over, but we want to talk in terms of multiplication here. That's how we get our equations out. Let's first confirm, maybe it'll be easier. Let's confirm that you're not adding the same thing over and over, because you might be. So what if I want to figure out 162 minus what is 108? You would do 108 minus 162. Maybe you have to take the calculator out. Right now I'm scratching for it for a while. It's negative 54. So I'm adding a negative 54 or I'm subtracting 54. Let's try 72 minus 108. 72 minus the number before it. That's going to be negative 36. So it looks like it doesn't have a common difference. It doesn't have a common difference. Okay, that means it's not linear. A common difference. That means it's not linear. So I know there's a chance that it can still be exponential decay. If I caught that I'm subtracting 54 each time, which is not true, but if I caught that, I would just say neither, because it doesn't have a common ratio or a common factor. It has a common difference. Therefore, it's a linear, not exponential. But the y values are going down, and they do keep doing that, so there's hope that it is exponential decay. Let's do 108 divided by 162. Now, the only thing here is, you really want to reduce this fraction. You want to see if this thing works out. I'll make it easier for you. I'll divide them by 2 first, 54 over 81. Eventually at some point, you got to know some of your multiples. I can divide them by 3. It might be easier to say divide by 9. You should know what 54 divided by 9 is and 81 divided by 9. And then I can divide these by 3. And I get 2/3. So that reduces to 2/3. Let's see what 72 over 108 reduces to. 72 can divide by 2, 108 can divide by 2, 36 over 54. You might see the same thing as dividing by 9 again. You're like, yeah, I can divide these by 9. So that's going to be 4 over 6, which reduces to 2/3. Okay, I'm on the right track. Now this should be enough normally. I don't think they'd normally trick you with the last one unless, I'm teaching you and I have a typo. But let's see how this one turns out. You might know you can divide, let's just divide, let's divide them by 2 first. Let's make it easier for you. And, we can divide these by 12, right? Or by 4, but let's do divided by 12, 2/3. So, 162 times 2/3 is 108, because 108 divided by 162 is 2/3. 108 times 2/3 is 72, because 72 divided by 108 is 2/3. And the last one, same thing, times 2/3. There's a common multiplier of 2/3. That would technically be your b value. And as we see a here again as being your y-intercept, your a value is 162. So if you want to write an equation, I know I still have to answer this, but if you want to write an equation, it's y equals 162 times 2/3 to the x power. Every time x increases by 1, you take 2/3 of your previous value and keep going. Yes, this is exponential decay. Exponential decay because y is, I don't want to say increasing. I mean, y is technically decreasing, but I don't want to say decreasing as in divided by. Y is decreasing by factor of 2/3. You're taking 2/3 of your previous number. That is what exponentiality is all about. Exponentiality is all about multiplying by the same number over and over. That's all it means. That's all it means. Don't make it more confusing than it should be. Now, as I'm going to jump to the next sort of problems in a bit here, you could write this as like y equals 162 times 1 minus 1/3 to the x power, which means you're taking 1/3, you're doing a 1/3 decrease. You're taking 1/3 off your previous value. If you wanted to round that value, that'd be like 1 minus 0.33, sort of. So it's kind of like so it's kind of like a 33% decrease of what you had before. So kind of interesting, 33% decrease, because I'm going to run into the next problems when I do that. Now, what if they asked you to extend this table? What if they asked me to figure out what happens when x is -1? What is y? Well, as I multiply by 2/3 this way, I divide by 2/3 this way. And you might not like dividing by 2/3, but that's the same thing as multiplying by 3/2. So I'm going to take 162 and I'm going to multiply it by 3/2. You might not like doing that either, but the good news is that 162 is being divided by 2 here. See, this is 162 times 3 all divided by 2. 162 over 2 reduces to 81. 81 times 3 is 243. So that would be the value of y when x is -1. You can go that way as well, and that might be something worth practicing and doing. Not for this problem, but if you ever wanted to extend a table or work on those, that's how you work with fractions, dividing by them. You multiply by fractions like that. Okay, last stuff for section 6.4. These are word problems. We're going to come up with a model, a function right here that represents something, and then we're going to come up with an answer for something else. You deposit $750 in a savings account that earns 5% annual interest compounded quarterly. Write a function that represents the balance after t years. What is the balance of the account after 4 years? Okay, so this one I will end up using the calculator for, just so you know, because we'll be doing decimal things and they get a little funky. And you're expected to be able to use a calculator on these and do pretty well. Before I talk about compounded quarterly, let's talk about this as if it didn't say compounded quarterly. Let's first make sure we get what's happening here. You deposit $750 in a savings account that earns 5% annual interest. Annual means every year. Once a year. Or yearly, whatever. Interest, like, hey, I'm interested in that. Interest is referring to a percentage increase. Percent increase. You know, when you put money in a bank account, your money grows. In a savings account, your money grows with a certain percentage increase, which is kind of nice. 5% is actually pretty large. I tell some of my students that my bank account, my savings account, I get 0.1% interest. I mean, that sucks. Like the most I can find online to get really is 1% interest. That'd be a lot better, 10 times more. This stuff really occurs for, I don't really know what kinds of banks, so to speak, but you can do it for mutual funds and stuff. But anyway, that's besides the point. You deposit $750 in a savings account that earns this much. Okay, deposit $750. This is how much you start with. It's a starting amount. Now, when it comes to what we're trying to do here, is we're trying to come up with a function. We're trying to come up with an equation that represents all this stuff that's happening. So, what we're really doing is we're really writing an equation that's like y equals a times b to the x power. Now, what you've seen me write in class, if you've seen me write in class, is I'll keep a here. My b value, I'm going to take 1 and add this value. And, now we're talking about t instead of x. So you might have seen this written here. This is kind of the same thing. You've seen me already write this now a couple times over here, the 1 minus, 1 plus, 1 plus. I didn't write 1 minus here, but, you've seen this now a couple of times. You've seen it actually take hold. This is how much I'm going to multiply by. It's still my multiplier. But the reason why we're writing it as 1 plus is because this 5%, b is not just 5%. B is a 5% increase. If you take a 5% increase of something, you might know that 5% is the same thing as converting to 0.05. But I don't want to just multiply my value by 0.05 over and over because that'll make it 5% of the previous amount. I don't want to take, I don't want to take 5% of $750 because that'll shrink my money a whole bunch. I don't want to do that. That's not what I want to do. I want to get 5% increase of. So take 5% of 750 and add to 750. Well, 5% increase is the same thing as 1 plus 0.05, which is 1.05. 5% increase is the same thing as 105% of. So technically, I'm going more than 100% when I do this. That's why this 1 plus is here. So my b value is actually 1.05. And that's, I'm going to write 1 plus 0.05 here still when I do this. But that's the inside part. 1 plus 0.05 to the t power. Now, A represents your starting amount. And it represents it because this is, when you deposit it, when you submit it to them, maybe the teller, the person on the other side is saying, All right, welcome to our bank. Thanks for opening up a savings account with us. When you put this in, let's start the clock. You are currently at year number 0, right? Year number 0. If this is after T years, and T is this thing right here, and we're talking about annual interest, then we're referring to the fact that that no years have gone by yet. After T years, we just deposited our money, and anything to the 0 power is 1, and we want this number to come back out. So 750 comes back out as a result of that. So the answer to annual interest for this thing would be 750 times 1.05 to the t power. That would be our function. That way, every time t increases by 1, every time we go another year, we can get 5% more than the year before. And that'll be sweet, and that'll be fine. Now, the problem with this is that this was not the actual problem. Like, this was not actually what we were being asked to do. So I'm going to leave this off to the side because I will use it later. But that's not what we were asked to do. We were asked to find 5% annual interest compounded quarterly. Compounded quarterly. Now, if it wasn't compounded quarterly, this would just be our answer right there, and you're pretty used to that. Here's what compounded quarterly means. First of all, quarterly means once every quarter of a year. That means 4 times a year. Okay. So compounded quarterly means what they're going to do is they're going to take your 5% and they're going to break it up into 4 equal parts. Now, this might be a time that you decide to use the calculator, but I think I know what this divided by 4 is. That's 1.25%. 1.25%. They're going to break up your percentage into 4 equal parts. So I did 5 divided by 4 right there. Okay. Because this times 4 is 5. Okay. So we break it up into equal parts. Now, what are we going to do with that? Quarterly means 4 times a year. 4 times throughout the year in even parts. So say every 3 months, because 12 months in a year divided by 4. So every 3 months, you are going to be doing another 1.25% increase. So if I were to kind of write this in a different way, I'll take this idea here, but I'm going to do 750 times 1 plus, I'm not just going to do 0.05 anymore. I'm going to do 0.05 divided by 4, which of course is those numbers. And I'm not just going to do t anymore. T may represent the number of years this goes by, but I need my exponent to represent the number of times I am increasing my amount every time I'm compounding my value. I'm going to be doing it 4 times a year every year. So if I do 1.25%, I'll be doing it 4 times more than I would have if I just compounded annually. So this becomes y equals 750 times 1 plus 0. This is 0.125 if you actually do the division there. So that is y equals 750 times 1 plus, times 1.0125 to the 4t power. That ends up being the model for this thing. Now this one compared to the one I wrote here in red, they do differ. This is straight up annually. This is compounded annually, and this is compounded quarterly. Now, the question becomes, what's the difference? What's the difference between these two? And I'm going to make sure to compute the difference here. And remember, this is the model that we're actually going to use. This is for part A. What's the difference? If this becomes 5% anyway at the end of the year, what's the difference? Well, I'm going to type out kind of a saying here, and I'm going to see if you can kind of really connect what it means when I do say it. When you take a percentage of something, taking the percentage of a larger number is larger than taking the percentage of a smaller number. Meaning the value that you get by taking that percentage is larger than before. See, when I subtract 20 from 74, and when I subtract 20 from 54, no, that doesn't really work. I guess subtracting a larger number is still large and subtracting a small number as well. But okay, the point The point is the difference between those numbers would still be 20. But here, if I take 20% of 100 versus 20% of, say, 20, see, 20% of 20 is the number 4. 20% of 100 is the number, 20. 20 is larger than 4. Not only that, but, I guess that's what I mean. So what am I saying with all that is that, well, first I'm going to start with 750. Remember, both these start with 750. Here, I am going to accumulate up to 5% throughout the year, but I'm going to do a quarter of that 4 times throughout the year. And I'm going to take 1.25% of 750. So here, I'm going to whip out the calculator for this part, because this gets kind of bizarre if I don't use this. I can't seem to clear that thing out. Hold on. Okay, I think it just needed a refresher. So let's say we do 750 times 1. Here, I'm going to start with this other one, 1.05 to the first power. After 1 year, I take 5% more of what I had before. Now I'm going to have $787.50 after 1 year with this model. So you might be thinking, well, if I do all of these spread evenly throughout the year, I'm going to get the same number. Well, here's the difference. The difference is that we are 1.0125 after how am I trying to say this? After 3 months, this is what I'm going to have. $759 and about 37 cents. Then after another 3 months, I'm going to multiply by this again. Now I'm going to do it again after another 3 months. And lastly, I'm going to do it one more time. $788.20. Well, 788 is a little more than that other number I had before. I have to see what that other number was. I forget. It's not much more. I agree. It's not much more. It didn't really do as much as I really wanted it to do. But that's, we're going to talk about over time. We'll see exactly what it is. So compare this amount to this amount. And what's the difference? It's only a 70 cents difference. It's not that different to you. You're like, no biggie. But you also have to remember this was only over the course of 1 year. We only did talk about compounding quarterly. It's not like we talked about compounding hourly. And that's kind of, relatively $750 is not that much in a savings account. So if you talked about $750 million, well, now the difference is, a lot. Now the difference is like $700,000 after 1 year. So obviously, look, it all depends on what your numbers are. But those two numbers differ. These were both after 1 year, and you saw this one had more. Now, how come? Well, it's because when you took 1.25% of your initial value, you've made it a bigger number, right? It became a bigger number, whatever it was that was above that. Now I'm going to take 1.25% of that number, and I'm taking 1.25% of a larger number than I am of 750. See, I'm not always taking 1.25% of 750. I'm doing 1.25% of larger number as I do it. So what happens is that taking the percentage of a larger number is larger than taking a percentage of a smaller number, right? When I take 1.25% of 750 and 1.25% of this number here, the difference becomes larger here because I'm taking the percentage of a larger number. Now, I know this all gets very confusing, and I know this does slow and bog down the video a lot, but I'm really trying to get the explanation down of what compounded quarterly is and why we do it and all that. Now, let me kind of answer the question here. What happens? What is the balance of the account after 4 years? So the balance of the account after 4 years, what we're going to do, and of course, I'm going to compare both of these in the end as well, but the black one's going to have to be the answer. So for part B, we'll get y equals 750 times 1.0125 to the 4 times 4 power. T is 4. T represents the number of years there are. And I'm going to compare it to this one. Y equals 750 times 1.05 to the 4th power. So again, why is this one 4 times 4? Why is that 16 here? Well, 1.0125 to the 16th. Well, because I'm doing this quarterly. I'm doing this once every 3 months. If there are 4 3-month periods in a year, that means 4 times every year. Times 4 years, I'm going to do this 16 times over the course of 4 years. 4 times for each year, every 3 months. So there are 16 3-month periods in 4 years. So that's where I'm doing the 1.12, or the 1.25%. This one I'm doing a 5% increase every year for 4 years, or four times. Both of them are for 4 years, but 4 times. So let's compare both of these answers here. Let's do the smaller one first, 1.05 to the 4th power. Okay, and I'm going to get $911.62. By the way, when we come up with these answers, it's good for me to talk about this rounding idea as well. I'm putting 62 and not 63. I'm not going to round up. And that's because I didn't yet get my 63rd cent. Now, if you're trying to withdraw your cash and the bank person gives you a feud with it, you're saying, come on, it's just a penny. I really need that penny. Maybe they'll give it to you. Maybe they'll find one on the ground and say, here, take that. But I don't have that 63rd cent yet. So I don't round. I just cut off whatever's on the side. Okay, and I'm going to do the same thing over here, no matter what it is. So this one here is 750. I haven't done this problem before. So 750 times 1.0125 to the 16th power. Now, this number should be bigger than 911. 914, that's not much bigger at all. So, hey, you know what? This isn't necessarily a very fun way of playing with one of these things, but that's all right. So $914 and how many cents? 91 cents, not 92. This is the answer. All this stuff was just to have some fun about annual interest. This is the compounded quarterly answer. So after 4 years, you'll have that. But I did want to compare these. You get about $3 more. After 4 years, you get about $3 more than you get there. And again, you're probably saying that's not that much. And you know what? I agree. That's not that much. It depends on how you're compounding. Again, we compounded quarterly. There's such thing as compounding monthly, weekly, daily, hourly, continuous compounded interest, or something like that as well. You'll get more money over the course of time, and it does actually grow to a substantial amount when you do talk about those kind of compounding things, especially, like I said, over the course of time. What if instead of 4 years, what if I talked about 40 years? So we did 160 here versus that other one that was, how much did I say? Over 40 years. So we'll call that a 40 right here. Compare these two. Okay, now it's more of a $200 difference, close to $200 difference. And, that seems to grow. And, of course, $200 over the course of 40 years, you're still like, that's not that much. But, again, remember, we only invested $750. So you invest. So 3 things come into play. Well, maybe 4 things. Here, hang on. Number 1, the amount you invest. Number 2, the time that has gone by. Number 3, the kind of compounding that you choose, like quarterly, monthly, whatever. Number 4, your percent interest. If your percent interest is larger, I think you'll see that take hold a lot more as well, too. This is only 5% interest. You might see something with 12% interest. So the final question here that people would ask is, why would you choose the annual interest option when you have something like this as well? Well, what you would end up doing with problems like these is, and if this was a real life thing, say that they gave you options, they wouldn't give you the same percentage for both of these. It's likely they might call this one 5.1% interest, or something different. They'll give you a larger interest option than this one, because this one has 2 good things going for it. Number 1, more money, and number 2, money faster, meaning I'm going to get money every 3 months instead of every year. So there are 2 benefits to going with that. So what they'll normally do is they'll offer options where if you do less compounding, they'll give you more interest, give you that incentive to do that, because then your money might grow. It just depends on the problem. I could probably show you some actual word problems that really do compare them. They'll say, this is the annually, this is the quarterly. They might say 4.9% is the monthly and stuff like that. Obviously I don't really have good values for you. And then they'll ask you which one's the best option after 20 years and blah, blah, blah. And maybe one's not a good option after 1 year, but it's a better option after 20 years. You just got to weigh it out and calculate it. So it literally is a real world problem when you do that. But anyway, so that's the answer there, $914.91, and there's the model for part A. This stuff was just to get it started. Okay, part B, or the second problem here. The value of a TV is $1,500. Let me put this off to the side. The value of a TV is $1,500, and its value decreases by 14% each year. Write a function that represents the value y in dollars of the TV after t years. Find the approximate monthly % decrease in value. Okay, so first and foremost, let's come up with part A, come up with that function. Now this says 14% each year. So 14% is 0.14 as a multiplier. Same kind of things we talked about before. 5% is 0.05, but we're going to decrease. So we're going to take 14% off the TV every single year. So this is going to become a y equals equation where instead of doing 1 plus 0.01 or 0.14, we're going to do 1 minus 0.14. We're going to raise it to the t value. There's no compounding taking place here necessarily. But we're going to be doing this because we need to take 14% off of the value. 14% decrease, 14% decrease in value as the television depreciates in value is 100 minus 14, which is 86% of. So every single year, the TV becomes 86% of its previous value. So that will be 0.86 right here. And it's probably just a better way of putting it. 0.86 to the t value. And then it starts off at $1,500 because we're talking about the value y in dollars of the TV after t years. So when the TV first comes out, no years have passed yet. And then 1 year will have passed eventually. But this becomes the model here for part A. Y equals 1,500 times 0.86 to the t power. Again, 86% of is the same thing as 14% off. So after 1 year, it becomes 86% of this number. After another year, it becomes 86% of that number. So, and going here, taking the percentage of a larger number is larger than taking the percentage of a smaller number. So if I take 86% of 1,500, that's going to be a larger difference than whatever 86% of the next value is. To kind of show you that, let me actually calculate it. Let's do 86% of 1,500 by doing 0.86. And that number is 1290. Now 1,500 minus 1290 is 210. So $210 off the TV after 1 year. Now I'm going to do 1290 times 0.86. And that's that number right there. So let's do 1290 minus 1109, 1109.4. That's $180.60 off. So you notice that the biggest drop in price goes from year 0 to year 1, and then year 1 to year 2, and this keeps going. So, we're doing this model here, and they are not asking us, find the value of the TV after 20 years, but let's do something like that. Let's find the value of this TV after 20 years times 0.86, and I'll raise it to the 20th power, just so you kind of get what we're doing here. Okay, now the TV's value is $73, and I don't know, maybe that sounds pretty reasonable, actually, as far as that. Now, what is it after 21 years? What I'm going to do is the same thing, only I'm going to raise it to the 21st power. And I want you to see what the difference becomes here, because it's substantially smaller. It goes from $73.40 to $63 and whatever cents. So it's only $10 off from 1 year to the next. So there becomes this diminished returns kind of thing that goes on. By diminished returns, I mean that, you're not getting more output for the amount of input that you're putting in. Meaning, me waiting a whole nother year to make this TV decrease in price is not going to be that worth it. I might as well buy it the year before because I'm only spending $10 more, and to me that $10 is not going to mean that much. Even if this was $73,000 for $63,000. Maybe $10,000 off isn't that much of a difference to you because before you were talking about a $2 million difference or whatever that was going to be, right? So, maybe it just doesn't mean that much in comparison to what we were talking about before. The biggest drops in price come from the very beginning. And if we look at this as a graph, it's an exponential function, of course, like all of these are, but this exponential function is positive exponential decay. Now, what that looks like is something, I don't know why that's happening a lot. What this looks like is something like this. Technically, I start at $1,500, and every year I take 86% of its previous amount. It's lessening a lot less than some other things are. Its asymptote is still way down here, but it's going to take a lot of years. It'll probably take 2 million years to get really close to that zero value because that this value doesn't just do $10 off each year. It does less. So just, it takes a long time. After some amount of years, let's say after 10 years, it's some amount. I don't know how much it was going to be. Let's say it's probably 400. I don't know how much it's going to be. But, 400. But anyway, so there's that stuff there, and this is exponential decay, and I wanted to make mention of this. How come? I think I just wanted to show that this value here is lessening, and it takes kind of a while to get there. Oh, no, the reason why I wanted to talk about this was a couple things. First of all, let's say this value was not when the TV first came out. Let's say this is just a value. This is just the value that you saw on a certain year, but the TV came out the year before. You could find out what the value was the year before by doing what? Well, here we're multiplying by 0.86. Now, here's where something's going to get really hard. Here we're multiplying by 0.86 each time, times 0.86, times 0.86. Here we got to divide by 0.86. Now, is the opposite, is a 4% decrease going one way, how am I trying to say this? If I'm doing a 14% decrease one way, would I do a 14% increase the other way? The answer is actually no. If I do 1 divided by 0.86, it is not 1.14. It is 1.162. It's a 16.2% increase, because this number divided by, let's see, how do I say this? 1 divided by this number, 1 divided by the number before it, is 0.86. Okay, just like 0.86 divided by 1 is 0.86. And just like 63 divided by 73 is kind of 0.86, all that kind of stuff. So it's more like a 16% increase. Kind of weird how you say that, but they're not the same thing. Okay, so that was one reason I wanted to say that. The other reason is for Part B. Part B is asking us find the approximate monthly decrease, find the approximate monthly percent decrease in value. So there are kind of two ways we can go about the problem. It depends. Let's say this is after year 1 and we're right here. After year 1, we're right here. Remember, this is a curve. This is not a straight line. What's the difference between a curve right here and a straight line right there? Well, straight line does this. It stays a little bit above it. So I don't know how they want you to answer this question. Are they saying, what if we drew a straight line from one to the next? And the reason why we draw a curve anyway is because it's not like they just decreased the value from 1500 to however much it was the next year, 1290, just after 365 days. Maybe over the course of the year, maybe every month they decrease that price. But they do it kind of in a progressive manner. So they can decrease it to that, to that, to that, all that kind of stuff. So you have either one of two ways of answering Part B, and to be honest, I don't know which one the answer should be, so I'm going to answer both of them and use them based on the color that you see there. One way is by following the exponential model, meaning by taking, which this is how I assume they mean it. You do 0.86, and instead of doing the entire 1 year, you do 1/12 of the year, because that's after a month. After 1 month, how much has it gone down by? And that would give you I shouldn't have put a 1 there. That's for the year. This is for 1/12 of the year. So that would give you the blue value right here. It's going to be a little bit smaller than the green's going to be. I'll show you the green one in a bit. So we'll do 1500 times 0.86. Whoops. 0.86 to the 1/12 power. Now remember, 1/12 has to be in parentheses for this to work the way you want it to. 1/12 power, and I get about, keeps happening, hang on. I get about $1,481, and this is where stuff gets a little shaky as well. Is it 26 cents or 27 cents? Now before you thought, yeah, let's just cut it off, let's make it 26 cents. But when something decays, I still have that struggle of asking myself, have we lost the 27th cent yet or not? Some people say yes, some people say no. And when I mean people, I don't just mean students, I mean even mathematicians and stuff. It's kind of debatable which way it is when we're talking about decay. If we're talking about growth and it grew to this, we haven't reached the 27th cent yet. The question here is, have we taken off the 27th cent already? I always argue one way or the other based on it. I think I'd say that you do take it off, so I'd probably err to that one, but either would be fine. Now, what's the other way of thinking about this problem? The other way of thinking about this problem is doing a full year, but instead of doing an 86% of, whoops, I just wrote that wrong. instead of taking 14% off, let's take a 1/12 of 14% off, like that. And let's raise that to the first power after a year. So I don't think they're asking for the problem to be this way, but that answer should be just a little bit larger right there. It's kind of the same thing as like the compounding interest, only it's like not interest, it's decay. So like compounding decay. Now 0.14 divided by 12 is that strange number right there. I'm going to do 1,500 times that number, times the previous number there. And that's after a year. It's going to get me 17.5. I must have done something wrong. Oh, I have to do 1 minus that. Thank you. 1 minus 0.14 divided by 12. And I'll do 1,500 times that number. So I don't think this is how they ask the problem here. I think that this is more about exponentiation than anything else. So 1482.5. So as I said, it's just a little bit taller, and it is. So that equals about 1480, well, it equals exactly $1482.50. So look, it only costs only like $1 more, so it's not like it matters that much. So after a month, they either knocked it down to this or that. I think they're referring to this one. And to be more specific, I bet it's 26 cents right here. I think they want you to talk about how we take off here. If you saw in, these problems over here, you saw that we're talking about divided by 8 and, minus 4 plus 3, all that kind of stuff. We're talking about exponentiation. You know what I mean? It's an exponential chapter. So we're referring to exponentiation items like those ones. All right, so we're done with the word problems there, those word problems. Okay, 6.5, solving exponential equations. Solve the equation. Okay, I'm going to throw out two properties here that we're going to be using. The first one is going to be if we have two items of the same base that are equal to each other, the only way that these exponents would actually give you something that equals each other is if the exponents equal each other. And it's true to go the other way as well. If a to the m equals a to the n, then m has to equal n. There's no other way around it. So I'm going to do this first problem here. 5 to the x power equals 5 to the 3x minus 2 power. The only way that this is possible for these two things to be equal with the same base is if x equaled 3x minus 2. 5 squared can only equal 5 squared. It can't equal 5 cubed. Those are two different values. Anyway, it just becomes an algebraic problem we solve for x. If I subtract 3x from both sides, x minus 3x is negative 2x. Divide by negative 2, I get x equals 1. To double check this one, substitute this here. 5 to the first power equals 5 to the 3 times 1 minus 2 power. And 5 to the first power equals 5 to the 3 minus 2 power. And 5 to the first equals 5 to the first. Again, the only way this works is if you plug in a value for x that makes the left number equal the right number. 5 equals 5. 5 doesn't equal, say, 25. That's not going to work. So there's that one. Okay, the next three problems are going to kind of focus on another set of property things. I want to keep this one in mind here. A to the m to the n power equals a to the m times n power. What we're going to do sometimes is we're going to have something written and appearing as a different base. We're going to be able to change the nature of its base. If the base before was a to the m, I want to change the base to just say a, for example, because maybe it can get me to match something, to match bases. See, I can't do this property unless the bases match. Bases have to be the same. So I can't do the property unless that happens. So, we have to get the same base here. The issue with this, of course, is they're not the same base. And, there is no base that really matches 3 to get to 1, but you can turn 1 into a 3. In fact, you can turn 1 into any of these numbers. You could turn it into 900. You just got to make sure that you raise it to the 0 power. So if I turn this into, because, anything to the 0 power is 1, of course, referring to a non-zero value. So I can do this. Say if 1's 3 to the 0 power, basically I need this to turn into 3 to the 0 power, right? If you think about it. So I need this to also be 3 to the 0 power. So that's what's going to get me 1. So we'll say x minus 2 is 0. Add 2, you get x equals 2. That makes sense. 2 minus 2 is 0. 3 to the 0 power is 1. That works out. Okay, this problem starts to tie into these properties right here. So 1 over 16 to the 3x power equals 64 to the 2 times x plus 8 power. This is all an exponent up there. What I need to do is make this power match this power, or make this base and this base match. And what you have to do is start to dig down and say, can I think of a number that I can raise to some power to give me 1 over 16? And can I think of the same number that raises to some other power that gives me 64? Two numbers that I can think of off the top of my head that I can do this with are 2 and 4. I know that both 16 and 64 are powers of 2, and they are also both powers of 4. You can do either. You'll get the same answer. Let me, I'll do both. Let me start with 2, probably the harder of the two. 2 to what power is 1 over 16? Well, what you might want to start to do is first say 2 to what power is 16? And that answer is 2 to the 4th. So if I write that inside there, that's going to get me started a little bit here. It's going to get me going with what I need to do. And 2 to the what power is 64? Well, again, this is maybe where 4 would have helped you a little bit more. But this is 2 to the 6th power. 2 to the 6th power is 64 times 2 to the x plus 8. Okay, now this stuff, I still have to keep transforming this one right here. This becomes 1 over 2 to the positive 4 is the same thing as 2 to the negative 4th. Notice that I didn't yet have my 2 in my numerator. I needed to have matching bases, and that's not going to work, right? That's not going to work unless I actually, take care of getting this in the numerator. So this becomes 2 to the, here, I'll leave it like this for a moment, 2 to the 6th times, or raised to the 2 to the x plus 8 power. Okay, now I'm going to use this property, this idea. I have exponent raised to exponent there. My bases kind of match, but right now this base is still 2 to the negative 4th. This is still 2 to the 6th. I want this base to just be 2. So now I can turn this into this right here. I can multiply by negative 4 by 3x. And I can multiply this 6 by, here, when I distribute this, 2x plus 16. Boom. Now I have matching bases. 2 to this equals 2 to that. And the only way that this thing works out is if that negative 4 times 3x equals 6 times 2x plus 16. And then we start to solve for x. That is a 12. I need it to be a 16. Then we need to solve for x. Negative 4 times 3x is negative 12x. Distribute. We'll get 12x plus 96. Subtract 12x from both sides. That's negative 24x equals 96. And divide by negative 24, I think we get x equals negative 4. I think that's what that value ends up being. So it's kind of a longer problem when we did that, but that's what we got as a result. I'm going to do this with 4 as well, and honestly, I think I like using 4 more in this case. Normally, it's better to use bigger numbers whenever you can. You just got to identify that that number works, right? Maybe you just know that 2 works in that case, but you didn't know that 4 worked in that case. I think 4 is going to work out a little better. So this is 1 over 16. I'm going to rewrite the problem a little bit. 1 over 16 to the 3x equals 64 to the 2 times x plus 8 power. I think that was it. I hope it is. Okay, this time we're going to use 4. So this will be 1 over 4 squared to the 3x equals, this is 4 cubed to the 2 times x plus 8 power. This becomes 4 to the negative 2nd power. And this one right here, I'm going to go and distribute the 2 already, 2x plus 16, and get that started. And now we get to play that multiplication thing that we did last time. 4 to the negative 2 times 3x equals 4 to the 3 times 2x plus 16. Okay, the bases match. Okay, so same thing. Negative 2 times 3x equals 3 times 2x plus 16. And see, the problem's not much better, but the numbers are a little bit smaller here. Negative 6x equals distribute 6x plus 48. Subtract 6x from both sides. Negative 12x equals 48. divide by negative 12, you get x equals negative 4. So no matter what you do, it kind of looks like the same amount of steps, but the numbers got a little smaller here and worked with me a little more. Regardless, we get x equals negative 4 when we solve for that. So we got to get the basis to match. Got to get the basis to match. Seems like that problem's a little harder than this next one here. Last one we're going to do is 27 to the 2x plus 2 equals 81 to the x plus 4. Now, try and find a number that you can have a base raised to this power. Same with this as well. I happen to know that 3 works. See, 9 doesn't work because you can do 9 squared here, but you're like 9 to what power gives you 27? You know what? Technically, you can do 9 to some power gives you 27. I think it's 9 to the 3 halves power. Like 9 to the 3 halves power, because that's the square root of 9 cubed. It's kind of weird. You can. It's better to just use other things. Like this is 3 cubed. 27 is 3 cubed. And 81 is 3 to the 4th. Okay. All right, so now just straight up do that multiplication. Power to power. It's not literally the power to a power, but 3 times 2x plus 2 equals 4 times x plus 4. So, therefore, same base now, 3 times 2x plus 2 equals 4 times x plus 4. Distribute. 3 times 2x is 6x, 3 times 2 is 6, so 6x plus 6 equals distribute. 4 times x is 4x, 4 times 4 is 16. Subtract 4x from both sides, subtract 6 from both sides, 2x equals 10, divide by 2, x equals 5. And again, you can double check that as needed. You can plug those in. That would be 27 to the 12th power equals 81 to the 9th power. Apparently those are the same. That's kind of big numbers. I don't know if your calculator can go that large for values. That is pretty big. Pretty big. Okay, there's 6-5. 6-6, geometric sequences. Now 6-6 and 6-7 kind of fall in the same vein, and problems that we've done before will tie into these pretty well. I want to differentiate sequences from functions, though. Decide whether the sequence is arithmetic, geometric, or neither. Explain your reasoning. If the sequence is geometric, write the next 3 terms. Okay, first of all, arithmetic is equivalent to linear. Geometric is equivalent to exponential. And neither, of course, is neither of those. A geometric sequence is a list of numbers where the values are separated by a common ratio. See, that sounds like exponential. An arithmetic sequence is a sequence of values that are separated by a common difference. See, that sounds like linear. So the only difference between sequences and functions, or you'll see that all the functions aren't written as a list. These are technically like the y values. These are like the y values for x values that start at 1. 1, 2, 3, 4, etc. So that's the first thing. They may appear as lists and not as tables of values. They can appear as tables of values, and in fact, I think on future slides, on future problems, you will see that they appear as tables of values. But here's something else you're going to see with these. You're going to see them always starting from 1. See, sequences, or functions, they don't really have a start. We saw them start from 0 quite a bit, like right here. We saw them start from 0 because they felt like it, but they could have started anywhere. Sequences start at 1. These are terms, term positions. The first term is 2. The second term is 6. The third term is 18. The fourth term. There is no 0th term. We will come up with some 0th terms. I'll talk about what that means, but it's a theoretical idea. It's not a literal one. There is no 0th term in a sequence, even if it follows the same pattern. So there is no 0. There is no negative. That's the first thing. The second thing that's different is there is only integer values terms, 1, 2, 3, and 4. There is no 1.5th term. There's nothing that would go in between. The terms are just integers, 1, 2, 3, 4, etc. See, when I mentioned the when I mentioned the TV thing right here, and I said, here's year 0 and here's year 1, there are values you can get in between. See, there may be a sequence for a TV that just says every year we change the value, and that's it. We don't change it every day or every month or anything like that, or just continuously have it decrease in value. We just change in value. But functions, you connect the dots. Sequences, you don't connect the dots. Sequences is just one value, and then the next, and then the next, and it doesn't care about the in-between. The in-betweens don't exist. So sequences start at 1, and there's nothing in between. It's just 1, 2, 3, 4, etc. And that way you can write them as a list and you'll always know what that means. So that's what they are, and a geometric sequence very specifically is exponential, linear, arithmetic very specifically is linear. Okay, so for something to be an arithmetic sequence, it would mean that it would have a common difference, which means that 2 plus something is 6, 6 plus that same thing is 18, 18 plus that same thing is 54. So is it arithmetic? You probably already are saying no, because 6 minus 2 is 4, and 18 minus 6 is 12. So already you can see that I'm adding 4 and then adding 12, and it's not the same thing. No, it's not an arithmetic sequence. You don't have to keep going. Once you see there is no common difference between the first two terms, you don't have to keep going. Was it geometric? Am I multiplying by the same thing over and over? And remember, we're never going to say divide. Okay, I will always say multiply with this, even if it's a fraction. So is it geometric? Let's do 6 divided by 2. Well, here I'm doing division, but I mean going from one value to the next. One value divided by the one before it, though, is 3. 18 divided by 6 is 3. So far, so good. 54 divided by 18, you can try it out. You're going to get 3. Yes, this is a geometric sequence. Yeah, I meant yes. This is a geometric sequence because you're multiplying by 3, going from one value to the next one term to the next term. So write out the next 3 terms. Well, the next 3 terms, they start from 54. And from 54, I'm going to multiply by 3. And then from that number, I'm going to multiply by 3. Now, I may use a calculator here. I'm going to try my best without it. You know I like to do that. Now, the thing that I'm doing right here is actually called using recursion. It's kind of interesting that I'm saying that before that part pops up, but this is technically what's called recursion. I am going from one value to the next, and I'm multiplying by something there. So you probably use recursion more than you know. So when we run into the recursive sequences, don't make it confuse you more than just the appearance of the notation. I'm also stalling and trying to figure out what this number is in my head. 486 times 3 is 1458. You know, I don't trust myself. Let me check with this. 486 times 3. 1458. Okay. That was a good year. I don't know what happened. Columbus might have been born. I don't know. Okay, so those are the next 3 terms. 162, 486, and 1458. Now, that's because it was geometric that they asked us to do that. I think they should have us do it as well if it's arithmetic, but knowing this is geometric sequences, you can probably say most of these probably will be geometric. I don't know. All right, next one. Is it arithmetic? Arithmetic? And again, I'm going to keep just talking the same way that I did last time, just in case you're uncertain of kind of what's happening here. 12 minus 3 is 9. 48 minus 12 is 36. That is not a common difference. No, it's not arithmetic. Is it geometric? We got to be dividing now to figure out, are we multiplying by the same thing? 12 divided by 3 is 4. 48 divided by 12 is 4. So far so good. 192 divided by 48. You know, I help you out a little bit here. It is 4. Let's go to the calculator. Yes, it's geometric. Yes, again. So geometric, write out the next 3 terms. And this time I'm probably going to go to the calculator. I don't want to spend more time. This video has already gone way, way, way beyond whatever. But if you're trying to learn it, I sure hope this is helping, because I'm exploring these topics for you. You know, we're really going above and beyond what we need to do sometimes here. So times 4, times 4, times 4. So 192 times 4. I'm just going to go ahead and do it here. 192 times 4. That number times 4, that number times 4. Okay, yeah, I didn't want to do these in my head. No purpose for here to do it in your head. So we got 768, 3072, and 12,288. All right, those are your 3 next terms there for this geometric sequence. And again, it's a geometric sequence because they have a common ratio. You multiply by the same number over and over. Okay, next problem. We got a 9, a negative 18, a 27, and a negative 36. There is one way for you to know off the bat, actually, that this is not arithmetic. An arithmetic sequence would have no way... See, an arithmetic sequence has a common difference and is linear. That means it can't fluctuate from negative to positive over and over again. It's got to either... once it hits negative from positive, it's going to stay negative and keep going largely negative. So I already know it's not that. Let's just see it. Let's still see, because there's still something to this that might make you go, yeah, that's interesting. Negative 18 minus 9 is negative 27. 27 minus negative 18, see, that's something I want to talk about right here as well, is that, you are subtracting every single time, even when you subtract negatives. Now it becomes addition, which is 45, and of course that means it's not arithmetic. No, not arithmetic. But what's interesting about it is if all these were positive, then yeah, you'd be adding 9 each time, plus 9, plus 9, plus 9. But it's not quite that. So is it geometric? Is it geometric? Are we multiplying by the same thing over and over? Negative 18 divided by 9 is negative 2. 27 divided by negative 18, it doesn't look like it's negative 2. So it doesn't equal negative 2, but if I reduce that, that would be negative 3 over 2. So no, it doesn't look like it's geometric either. Yeah, that's kind of all I wanted to say on that one. But check this out when I do this next one. Negative 36 divided by 27, that's negative 4 over 3 as it reduces. It's kind of interesting. You probably see what's happening here. Negative 2 is negative 2 over 1. So this goes from negative 2 over 1 to negative 3 over 2 to negative 4 over 3. This number goes down there, and the next number comes up. See, the next number we'd be doing is 45 over negative 36. And guess what that is? Negative 5 over 4. So even though there's no common ratio, the ratio does have a pattern. It's kind of an interesting pattern. I like it. It's kind of cool. And they do stay negative. Notice how this thing went from positive to negative to positive to negative. So it had an opportunity of being a geometric sequence with a common ratio being negative. It wasn't common. The ratio had a nice pattern, but it wasn't common. So it's not geometric either. It is neither. Not geometric. The answer here is neither. Now, they're not asking you to list out the next 3 terms, but I bet I could. See, you kind of know the pattern if you say, it's kind of like doing plus 9, but you switch from positive to negative. Like 54 plus 9 is 63. So it would be like, this was negative, so positive, negative, positive. I bet these would be the next 3 terms. And I bet I could follow even this pattern and figure that out, exactly what that thing was. They're not asking you to do that, however, and it's probably a little above and beyond what we're doing, especially when it comes to writing an explicit formula. We wouldn't be able to do that because it's not a geometric sequence. Okay, going off of what I said last time and probably having you make sense of the fact this couldn't possibly be arithmetic, it's no way I'm subtracting the same thing one to the other, is that these signs alternate. So there's no way this is arithmetic. Also not arithmetic, but is it geometric? 375 times what is negative 75? Let's do negative 75 divided by 375 to figure that out. Okay, well, I know for sure these can both divide by 25. So negative 3 over 24 and 12, 15. Negative 3 over 15, which is negative 1 over 5. Okay, so negative 1 over 5 for that one. Let's check 15 divided by negative 75. You can divide those by 5 if you have trouble there. 3 over negative 15, which of course also there is negative 1 over 5. All right, so far so good. And the last one, negative 3 over 15, as we saw the last 2 times, is negative 1 over 5. So common ratio. Common ratio, it has a geometric sequence, or it is a geometric sequence. It has a common ratio. So geometric. I don't know why I said yes for these. These are geometric. Yes, yes, yes. So geometric, what are the next 3 terms from negative 3? Well, our ratio is negative 1/5. So from negative 3, I'm going to find 3 more terms. I'm going to multiply this by negative 1/5, multiply that by negative 1/5, and multiply that by negative 1/5. Negative 3 times negative 1/5 is positive 3 over 5. 3/5 times negative 1/5 is negative 3 over 5 times 5 is 25. And negative 3 25ths times negative 1/5 is positive 3 again over 125. Basically 5 squared, 5 cubed, like that. And it keeps going. And those are your next three, and like I said, it keeps going. So it looks like the 3 kind of stays on top from there, and the sign alternates from positive to negative to positive. All that. So those were extending those, determining the sequence. We found common ratios with them. We didn't talk about term number 1 really, or term number 0 at all, but I think that's coming up next for geometric. Okay, write an equation for the nth term of the geometric sequence, then find a sub 9. Now the formula for a geometric sequence is a lot like the formula for an exponential function. Here's exponential function, here's geometric sequence. You can either write it like this, and you're like, that doesn't look like that at all. Well, it kind of does. I'll talk about why. I'll actually refer to this one more so. I know people have trouble with this notation, a sub n, but if you've done arithmetic sequences before, then you have seen it. By the way, some things, even some of my old videos, use t of n. So it looks like this. Instead of a sub 1, it becomes t of 1. Some books use this, some worksheets use this, some answer keys, whatever use this. So if you see this as well, this is the exact same thing. T of n equals t of 0. I'm personally not going to be using it, but I could point to some old videos that do use it. Okay, so these ones right here. Now this looks a lot like this one here. We're just changing out y for a sub n, a for a sub 0, b for r, x for n. So when we find the nth term, we're looking at it like this. So this is no different than exponential sequences. I mean, I need to make sure that you understand that. Geometric sequences are exponential functions, with the exception of we start from 1, we count up integer values, and there's nothing in between. So there's no 0, even though I can reference 0. We can find it, we can do something with it, but it's the same thing. So going back to it's the same thing. Let's say you didn't want to look at it this way. Let's say you wanted to use a table. And you called this x, and you called this y, and this was 1, 2, 3, and 4. Well, when we did y equals a times b to the x, all we had to do was find out the multiplier and the y-intercept. Now, I don't have my y-intercept listed here because I start at 1, but I can find the multiplier. They tell us these are geometric sequences, so I'm not going to spend time figuring out what the ratio is, or I'm not going to confirm that they have the same ratio. I will just say, if I know it, I know it. This is times 4, times 4, times 4. So my r value, my b, like my r, is 4. Every time n or x increases by 1, I'm multiplying by 4 again. Now, if you want to find out one with the a sub 0, or your y-intercept right here, what you would have to do is go 1 back. For x equals 0, or n equals 0, divide by 4 this way, multiply by 1/4, and 1 divided by 4 is 1/4. So a sub 0 is 1/4, that's the 0th term. If you want to just write a sub 1, that's the first term, that's 1, and that's totally fine. So you can write your equation one of two ways. Either a sub n equals a sub 1 times 4 to the n minus 1 power, or a sub n equals 1/4 times 4 to the nth power. Either or is a proper answer. So what do these two things mean? Well, let's start with this bottom one. This is a sub 0. This is the one that doesn't actually occur in the sequence. Let me kind of erase everything here. But this is the one that actually doesn't occur in the sequence, this 1/4 sticking out right here. It's not actually part of the sequence. It is the 0th term. 1, 2, 3, 4. If I want to get to the first term, I'm going to multiply by 4 once. If I want to get to the second term, starting from here, I'm going to multiply by 4 twice. Third term, 3 times. Fourth term, 4 times. Fifth term, 5 times, etc. So the number of times I multiply by 4 also matches the term position. Again, fifth term, 5 times. 10th term, I multiply by 4 10 times. 100th term, 100 times. A million terms, a millionth term, a million times. So the term that I'm looking for matches the number of times I multiply by 4. That's why I like this one. That's why I offer it and use it. I know your book doesn't seem to really mention that one. It kind of only mentions the top one. But the term that I'm looking for, the term value, the term position, represents the number of times that I multiply by 4, because 1/4 is not a part of my list. So when I find the first term, I'm multiplying by 4 once to match that. Now, what does this one say? Well, this one says I start from the first term. So if I start from the first term and I want to multiply by 4 to find the second term, I'm only multiplying by 4 once to find the second term. See, once to find the second term. Those are two different numbers. To find the third term, I multiply by 4 twice. 4, 3 times, 5, 4 times, 6, 5 times, 100, 99 times, right? I'm at the first term already. So to go to the 100th term, I got to multiply by 4 99 times, not 100 times. I'm already at the first term. 1,999,999 times. If I want to find the value at term n, I'm going to multiply by 4 one time less than the term number. Again, 100, to find the 100th term, I'm going to multiply by 4 99 times, not 100 times. Because I'm already at the first term. I don't have to multiply by 4 by anything to get the first term. I multiply by 4 0 times here. So that's the explanation and the difference between the two. I know the notation's weird, but if you kind of know the formula, it makes sense. Furthermore, if you really tie it in with exponential equations, I think you're really going to get it. But then you'd have to either get the 0th term or write it here. See, what's the difference between 1/4 and 1? 1 is 4 times more than 1/4. So what's the difference between this equation and this equation? This equation is something that's already 4 times larger, but I'm not going to multiply by 4 as many times. I'm going to multiply by 4 one less time. This thing's 1 time smaller, or 4 times smaller, but I'm going to multiply by 4 one more time than I will up here. I know the wording's weird. You got to kind of say it out loud for yourself. You got to test them and do all that. Now we got to find a sub 9. So find a sub 9. Let's use both equations here and kind of see that they give you the same answer here. A sub 9 in this first equation, it'll start from 1, and I'll multiply by 4. I'm not going to multiply by 4 9 times, though. I'm going to multiply by 9 minus 1 times. See, I'm trying to find the value of the 9th term, and I'm starting from 1. From the first term, excuse me. So I'm starting from the first term. So to reach the 9th term, I'm only going to multiply by 4 8 times. Now, I don't know what 4 to the 8th power is. This is settled with the calculator. So I'm not going to write that 1, because I know that that's 1 times anything is just that number. 4 to the 8th power is 6, 5, 5, 3, 6. So the 9th term is 6, 5, 5, 3, 6. A sub 9. Okay, what if I instead use this one? A sub 9, equals 1/4 times 4 to the 9th power. See, this one, I'm starting at the 0th term. So to find the 9th term, I got to multiply by my number 9 times. That makes some sense. So I should be getting the same answer here, times 4 to the 9th power. And I should be getting 6, 5, 5, 3, 6, and I do. So these are both, they're not the same equation, but they both represent the same thing. They are visually different, but they do give you the same exact thing. Remember, if you understand what exponentiation is, it's the number of times you multiply by something. There you go. Okay, now what's another way I could have done that problem? I already know the 4th term here. Now this is more referring to what are called recursive ideas, but I could multiply by 4 here, get that number, multiply that by 4 for the 6th term, times 4 7th term, times 4 8th term, times 4 9th term. It's probably a little too far out of the way to do it. If they asked just for the 5th term, probably would have just been easier to take 64 and multiply it by 4. Just depends on what the problem is, or what they're asking for. Okay, next problem. We need to determine, well, we know it's an a geometric sequence here, so if you kind of know what 1 multiplies by, all of them multiply by the same thing after that. 5 times negative 2 is negative 10, times negative 2 is positive 20, times negative 2 is negative 40. So my common ratio here is negative 2. Excuse me. Now my a sub 1 value is 5. It's the first term. The value of the first term is 5. So I can just write out my formula like this. 5 times negative 2, parentheses are so important for this one, to the n minus 1 power. If you want to write it with the 0th term, you can. Just note that to find the 0th term, you got to divide 5 by negative 2. It'll be negative 5 halves, and you'll work from there. I'm going to go ahead and just use this one this time. See, the reason why 0th term is not very fun to do with these ones, whereas for arithmetic sequences, normally it's not that bad, is these can normally turn into fractions when the rest of the sequence maybe isn't a fraction. So people just don't like to do that. but they also don't like to look at this. So it's really your call. I'm going to use this time, though. Let's find a sub 9. A sub 9 is 5 times negative 2 to the 9 minus 1 power. Again, this is the first term. I'm going to multiply by negative 2 8 times total. So 5 to the negative 2, or times negative 2 to the 8th power. Now, I happen to know that negative 2 to the 8th power is 256. So I could do 5 times 256, and let's see if I can do that without the calculator. That would be 1,280, I think. 1280. I sure hope that's the right answer, otherwise, because I'm trying to not check the calculator this time. I think that's right. No, it's not. Hang on. No, it's not. Wait, yes, it is. Yes, it is. Yes, it is. I trust it. Okay, I think that's right. Now, this was positive. This was positive. Negative 2 to the 8th power is a positive number. The first term is positive. The third term is positive. Fifth term is positive. Seventh term is positive. Ninth term is positive. The odd terms apparently are positive. The even terms are negative. Remember, this isn't the 8th term. It's the 9th term. This is the number of times I multiplied by negative 2. Okay, the last one they also say is geometric. Now, you're trying to find out what the sequence is here, what you're multiplying by, what that common ratio is. Understand it's the same number each time. They tell you it's geometric, so we already know that. So why should I do 162 divided by 486 when I could take a smaller set of numbers like 18 divided by 54 to figure out what that ratio is, right? What am I multiplying 54 by to get 18? Let's do 18 divided by 54 to figure it out. Now, maybe you're like, all right, let's divide them by 2. Let's divide these by 3. Let's divide these by 3. Okay, 1/3. It looks like that's my common ratio. My R value is 1/3. That's what I'm multiplying by each time, going from one value to the next to the next. This is my first term. A sub 1 is 486. Now, let's say you don't like this way that you write it. Instead, you wanted a sub 0 this time. If you want to do a sub 0, you better take 486 and divide by 1/3. That's not the same thing as dividing by 3. In fact, it's the exact opposite. Dividing by 1/3 is the same as multiplying by 3. So maybe you want that number just because. Maybe you just don't like that other formula. You're really used to y equals ab to the x, and you had to find your y-intercept, and you had to do it this way. Well, this times this is 14... 86, 40, 50, 58. Did we have this number before? I think we did. 1458? I think so. I hope so. I will double check because I'm going to run the calculator for some other... Actually, no, I'm not for the next 3 terms. Oh, to the 9th. Yeah, I might. All right, so your a sub n equation, I'm going to start with a sub 0 times 1/3 to the n power. Okay, so there's the equation. Now I could have done 486 times 1/3 to the n minus 1 power. Still going to get the same answer no matter what I do. Okay, now find a sub 9. So last part of this, a sub 9 equals 1458 times 1/3 to the 9th power. Now, I know you can type this in your calculator, and I'm going to give you a heads up here. It looks like we're going to get a decimal value, because I'm going to play with this recursively first and then confirm the answer that we get. Times 1/3, a third of 18 is 6. A third of 18 is 2. Excuse me, a third of 6 is 2. This is 1, 2, 3, 4, 5, 6. 3 more. 7, 8, 9. A third of 2 is 2/3. A third of 2/3 is 2/9. And a third of 2/9 is 2/27. So this is your answer, 2/27. In the calculator, if I type 2 over 27, I also want to figure out what 486 times 3 is. Okay, it is 1458. Awesome. 2 divided by 27 is that number there, 0.704, 704, 704. Excuse me, 074, 074, 074, and it rounds after that. So 0.074 repeating. So I'm going to write that because I have to remember it for what I do. So this will become 0.074 repeating. That'll keep repeating itself. So when I go to the calculator here and I want to do This instead, 1458 times 1/3 to the 9th power, I should be getting the same decimal. Okay, cool. So I got the same decimal. Now, what if they asked you to write it as a fraction? Well, these calculators do have a way of doing that. In here, I hit the math button in this fraction thing, and I know you probably don't have a graphing calculator to do that, but there should be one where I don't know where it is. Probably somewhere up here. You'll see something that says F and D. It says like fraction to decimal. It's something like, maybe something like F, D or something. You can find it, and you can probably do the same thing. You'll get 2/27. So if they're asking for that, you can do that, of course. And look, that wasn't too hard to do with the fraction if I went for the recursive approach, which I believe recursion is what I'm going to be doing next anyway. So last thing I just want to mention for these geometric sequences, when we found the equation for the nth term, these are called explicit equations. What explicit equations are using the term position to find your value. I literally use the number up here, 1, 2, 3, 4, 5, or the 9, the 9th term. I use the number 9 in my equations here, and I used it up here and down here. I'm using my term position to actually calculate my value. That's what an explicit formula is. A recursive formula uses the previous y value to get the next one. Now, explicit makes more sense with the equations that you write. You're probably more used to seeing them that way. And in fact, when you're trying to find a large term like a of 900, you probably want to use that. I probably wouldn't want to do this 900 times to figure it out. But the recursive one is something that you probably do in a more practical way. If I want to find out the 5th term, I'm going to take this times 4. So you're probably fine with doing recursion, but the question is, are you good with their equations? So let's find that out. This is the last section, recursively defined sequences. Write the first 6 terms of the sequence, and what you have is something that looks very weird. And in fact, when I wrote this in class, I wrote it a little bit differently. They do mean the same thing here. First of all, you have to understand what these things mean, a sub n. A sub n means the value of term n. So if n was 2, it's the value of the second term, value of term 2. A sub n minus 1 is the value of term before a sub n, or before term n, I guess. So it's the one before it. It's, like here, if this is my a sub n, then this is my a sub n minus 1. Because this is a sub 4, and this is a sub 4 minus 1, a sub 3. Right? Technically, this would be a sub n minus 2, stuff like that. Whoops. So that's how that's written. Now, when I wrote it in class, I wrote this n plus 1 on this side and a sub n on this side, and it means the same thing. A sub n plus, if a sub n means the value of term n, a sub n plus 1 is the value of the next term, the term after n. So it doesn't matter how it's written. You can either write it like this or that, and you're going to get the same thing. So, I kind of prefer writing it this way, and here's why. Because we're starting, they give us a sub 1. If a sub 1 is 4, I don't want to try and use this formula and say a sub 1 equals a sub 1 minus 1 plus 5, because I don't care what because I don't know what a sub 0 was, and frankly, I don't care. Right? If a sub 1 being 4, I have to use a sub 0 for that. I don't really care about that. So, whereas this book spelled it out like that, I'd rather go the other way. I'd rather start with a sub 1 and get the next term. To do a sub 2, understand that that is a sub 1 plus 1, which is, we know based on this equation here, it's taking a sub 1 and adding 5 to it. Now, I know this looks very weird to you. You're like, what the heck is going on here? Well, I'm just using this to get this formula. To find a sub 2, I'm going to take a sub 1, and I'm going to add 5 to it. So I kind of get to skip this part in the middle and go straight from here to here. Now, a sub 1 is 4. A sub 1 is 4. So a sub 2 is 4 plus 5, which is 9. A sub 1 is 4. A sub 2 is 9. 4, 9. Now, to find a sub 3, I'm going to take a sub 2 plus 1, which means I'm going to do the a sub 2 plus 1, which is a sub 2 plus 5. right? The value of the next term is the value of the term before it plus 5. So a sub 3 is a sub 2, which is 9, plus 5, which is 14. So this one's 14. Now, you can probably see how this pattern's working out every single time you're adding 5 to the previous value. Well, that's exactly what this equation says, right? I mean, it doesn't look like it. This looks like, a lot of stuff right here, right? And you're like, I have no idea what's going on here. But that's what this says. To find the value of the next term, take the term before it and add 5. That's what this one says too. To find the value of the next term, take the term before it and add 5. I just don't like using a sub n minus 1 because if we start with a sub 1, I'm not going to use a sub 0 in it. A sub 0 doesn't even occur in sequences, so I'm not even going to bother with that. I'll just start with a sub 1. So I'm going to find the 6 terms here, I'm going to keep adding 5. So you know that this is how we sometimes treat things. Now, this is not a geometric sequence. This is an arithmetic sequence because it has a common difference. So, I mean, understand that as much as I've been treating geometric sequences this way, or exponential functions this way, this is not exponential. This is linear. It's an arithmetic sequence. It's an arithmetic sequence because of the common difference. I'm adding a number over and over from the term before it. So it's not very hard to do when it comes to this kind of thing. You just got to make sure that you make sense of how to read this or this. Now, you can't do this. You can't add 5 to a previous number unless you know a number to start from. So I started from a sub 1. So whenever you write sequences, because we're going to do it on the next slide, whenever we write equations for these things, we have to give them a starting value. Even if you give them a sub 2, what if they started with what if you start with a sub 2 equals 9? Well, I can do that and add 5 a couple times to do there, and I could subtract 5 to find a sub 1. Maybe this equation would make more sense then to do something like that. But they didn't. They'll normally give you a sub 1. That's generally how it's going to look. Okay, this one, the first term is negative 4, and we got to find the next terms. To find the value of the next term, I'm going to take the value of the previous term, and I'm going to multiply it by negative 3. Now, again, I would preferably write it like a sub n plus 1 equals negative 3 times a sub n. Now, this is multiplication, right? That's what's in between there. Even though it doesn't say it, you kind of have to know that. So, again, to find the value of the second term, I'm going to take the value of the first term, the 1 plus 1 right there. I'm going to take the value of the first term and I'm going to multiply it by negative 3. So a sub 2 is going to be negative 3 times the first term, which is negative 4. So a sub 2, therefore, is positive 12. Then to find the value of the third term, that's the term after a sub 2, which means I'm going to take negative 3 and multiply it by a sub 2. So a sub 3 is negative 3 times 12, which is negative 36. So this one becomes negative 36. And again, hopefully you start to see the pattern. Hey, you're multiplying by negative 3. Well, it says that in here, right? Negative 3 times your previous term. So you don't have to write out this kind of work if you can interpret what the equation says. To find the value of the next term, I take the term before it and multiply it by negative 3. So that's how we're doing these ones, just like we did the previous ones. We got to write the first 6 terms. I may have to resort to the calculator depending on how large these get. We'll try not to. I don't think you're unallowed to, depending on what's there. Times negative 3. So I know this will be positive. The next one will be negative. The next one will be positive after that because we're multiplying by a negative. This is positive 108. This is negative 324. And this is positive 900 and I think 72. So they're the first 6 terms of this sequence right there. That is a geometric sequence because I'm multiplying by the term before it. It is a geometric sequence. Okay, this last one, I'm not going to do all this mumbo jumbo on the bottom, but I do like to rewrite it as a sub n plus 1 instead of a sub n. That's just a personal preference. A sub n plus 1 equals negative 1/4 times a sub n. So what this says is to find the value of the next term, you take the value of the term before it and you multiply it by negative 1/4. You're taking a quarter of it and it's alternating its sign. Now we're starting from 32. Times negative 1/4. That's the same thing as dividing by negative 4. Dividing this by negative 4 is negative 8. Dividing that by negative 4 is positive 2. 2 divided by negative 4 is the same as negative 1/2, so the next value is negative 1/2. Negative 1/2 divided by negative 4, well, this is where it might be easier to say times negative 1/4. Negative 1/2 times negative 1/4 is positive 1 over 8. So this becomes 1 over 8. And 1 over 8 times negative 1/4 is negative 1 over 32. It's kind of cool with this one here because you're really seeing that, see that reciprocity in the oppositeness? 2, negative 1/2, negative 8, 1/8, 32, negative 1 over 32. Those numbers tie in and then they have the opposite sign. So I kind of like that one. It's cool. It is geometric. Even if you said we're dividing by 4 here, or negative 4, you're really multiplying by negative 1/4. It does have a common ratio. It is geometric, and that's what they want us to do. So again, this recursion idea is really nice and clean when it comes to finding the next value from the value before it. The two issues would be, number one, what if they asked us to find the 100th term using this? Well, that would take a long time. Number two, the equation looks weird, right? This looks really weird. Look, I know that this looks really weird as well. It's not that this looks much better. This looks okay because it reminds you of this. But we don't normally see equations like this, right? We don't normally use this recursion idea, find the value of the next term and the value of the term before it. We say it, but we don't write it like that. So I can understand why that will look weird, and especially there's a comma, there's this stuff right here, extra information. Well, we're going to start doing that. We're going to now write some equations. It's one of our, I think this is our final slide coming up. Yeah, okay, this is our final slide. Write a recursive rule for this sequence. So what we got to do here is, first of all, establish whether this is arithmetic or geometric. Some of them, sometimes they're neither, but we need to do recursion here. We need to be able to take the term before it and apply something to it. So what's going to work for all these really well to start with is write the first term out. A sub 1 equals 5. Even this one, a sub 1 equals 3. Why am I doing this? Because this is a part of your equation. You saw it. A sub 1 equals 7. You saw it in this previous thing. All these say what the first term is. Because you can't add 5 without knowing what you're adding 5 to, or multiply by negative 3 without knowing what you're doing it to. So here, I'm going to start from 5 and then either add something or multiply by something. At least that's the idea. So here, I'm not going to spend too long on this. 12 minus 5 is 7. 19 minus 12 is 7. Minus this is 7. Minus this is 7. It looks like we're adding 7 each time. So to find the value of the next term, you take the value of the term before it and you add 7, starting from 5. So a sub 1 equals 5, and then to find the value of the next term, you do it like that. And that would be your answer. That's the equation. Now, if there's like a back in the book way of doing this because the problems were presented like a sub n and a sub n minus 1, this is also an accepted answer. A sub n minus 1 plus 7. And that minus 1 is a part of your subscript. You're not actually subtracting 1. You're doing the value of the term before it. So that one's okay as well. I'm personally probably going to write these mostly like that. And again, the reason why is because if you're trying to find a sub, you know what? It doesn't necessarily matter. But I'm not going to use a sub 0, so I don't want to think of a sub 1 minus 1 ever. It's just a personal thing. Okay, that was an arithmetic sequence, and that had that rule. I was adding 7 each time. Okay, this one, it looks like kind of more of the same. It looks like we're adding 5 plus 5 plus 5 plus 5 plus 5. Also an arithmetic sequence. So to find the value of the next term, I take the value of the term before it right here, and I'm going to add 5. Not the term before it, but the current term. Next term, current term. Boom. And again, you could write it like that, n and n minus 1. Okay, this one right here, plus 3 plus 6. Ooh, it doesn't look like it is arithmetic. Okay. How about times 2? Times 2, times 2. Yeah, it looks like it's geometric. Times 2, times 2. So I'm doubling my amounts here. So to find the value of the next term, I take the term before it, and I'm going to multiply it by 2, starting from 3. And again, that's kind of all you're doing here. You're writing out what do you do from one y value to the next, or one a sub, whatever. It's the same thing as we've been doing since the very beginning when I was using tableless graphing or graphing with the table. What was the pattern? And that's what you're finding out. It's just a list. This 29, this isn't a 29. This should be a 19. I'm sorry. Either way, it was neither arithmetic nor geometric, but this should be a 19. Let me do that one more time. Minus 1. How about this? Plus negative 1. Plus negative 1. Plus 7. Plus 6. Plus 5? Nope, plus 13. No real pattern here that you can like see how we're going from one number to the next. I mean, yeah, well, I guess you could. You could say 7 plus 6 is 13, negative 1 plus 7 is 6, and you can do things with that. You can keep determining the rule there, but we got to write a rule for this. But I do notice that there's a plus 7 here and there's a 7 here. And there's a plus 6 here and a 6 here. This one takes a while to come up with. It's apparently very similar to something like a Fibonacci sequence, which is adding the two numbers before it, which is what we're doing, but it's not the Fibonacci sequence. Okay, so you kind of see that, and even if we had a 0th term, you'd kind of understand maybe that would have been negative 1. For the same reason, we'd be adding negative 1. Now, we're not doing that, and we could find out the next numbers here. Let's continue this list a little bit. If here we did 7 plus 6 is 13 and 6 plus 13 is 19, 30 plus 19 is 32, then here we do 19 plus 32, which is what, 51? And then 32 plus 51, which is 83, and so on and so forth. So we can continue it. Now, how do you write that? How do we write that? Well, we're starting from a sub 1, which is 7. Okay. Now, this one's kind of strange. I think we need two terms. We need a sub 1 and we need a sub 2. Because this completely relies on, it completely banks on the two terms before it. So if I'm going to write an a sub n plus whatever, this time I'm going to find the term that's after, two after the first term. To find the value of two terms ahead, I got to take the value of the first term, or the thing two terms before it, and add the one that's just one before it, like that. And I think that ends up being your sequence, and I think that ends up being your equation. We can kind of see if it works. We'll try and plug some things in, because this is kind of my first time. I saw it and said, I think I know the pattern. The problem was the typo. That was my fault. I just typed it wrong. So let's see if that works. So now here's a sub n. So let's say I call that n1. So a to 1 plus 2, not power, a sub 1 plus 2 equals a sub 1 plus a sub 1 plus 1. Let's see if that works. A sub 3 equals a sub 1 plus a sub 2. A sub 3 equals 7 plus 6. So a sub 3 equals 13. Okay, so that seems to work out. And then we do a sub 4. A sub 4, this would be a sub 2 plus a sub 3, so it would be 6 plus 13, which is 19. So yeah, it looks like that one works out for the equation. That one was pretty robust. There's a lot to do there, very difficult. But that uses recursion fully, and guess what? You can't write an explicit formula for this. Well, I take that back. Maybe it's possible. But it's not going to be as simple as what we saw before. It doesn't just use that kind of recursion. Now, this is not arithmetic. And it's not geometric. It's just recursive. It's just a recursive equation. There's nothing, it's close to arithmetic because of addition, but you're adding the number before it. So arithmetic needs a common ratio. This one varies, obviously, and it depends on what's before it. It is very much recursive, close to Fibonacci sequence. The Fibonacci sequence is this. It does the same kind of thing, only it starts at 1. 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. There's some stuff on the Fibonacci sequence that occurs in real life, like naturally and stuff, and it actually has a reason besides referring to recursion. The first term of the sequence is 8. Hey, a sub 1 equals 8. Each term of the sequence is 5 times the preceding term. Write a recursive rule and an explicit rule for the sequence. Okay, first I'm going to start with the recursive rule. To find the value of the next term in a sequence, I will take the term before it and I will multiply it by 5. 5 times larger the previous one. So there's a recursive rule starting from a sub 1 equals 8. And I need the a sub 1 equals 8 to expand that. Write an explicit rule. Well, I can kind of do this one of two ways. You might, let me first by writing a little bit of numbers in the sequence. A sub 1 is 8, A sub 2 is 5 times 8. A sub 3 is 40. 5 times 40. A sub 4 is, the fourth term is that times that, 1,000 times 5, and then 5,000. And you can see, you can really find those pretty easily. And you can say we're multiplying by 5. Times 5 times 5. If you need to go to something else that you've seen before, why don't you go to this? Times 5 times 5. And we know that in this thing, this is when x is 1 and 2, or n. 1, 2, 3, 4, and 5. So, and we know our first term is 8. Notice 5 represents the common ratio. This is your common ratio. Whether or not you saw it here, whether or not you saw it here, you can probably see it right there. There's your common ratio, and we know our a sub 1. So your equation, you can write a sub n. You take the first term, and you multiply it by your common ratio, 1 time less than the term you're looking for, like that. Or we can find term number 0. We multiply what number by 5 to get 8? We'll divide it by 5 to figure out. That's 8/5. So to find term number n, you start from 8/5 and you multiply by 5 n times. Either or, you get that answer. That's explicit. This is a geometric sequence because you are multiplying. What else did I want to say about this one here? I don't know, I kind of feel like that was it. I need to wrap this thing up. This has gone way above and beyond, right? But anyway, from recursive to explicit, you can come up with one. As long as you recognize that's the common ratio and recognize it's geometric, you can jump straight into there from that. Use the first term, have the common ratio, and jump from there. Okay, well, hey, I hope that you learned something here because there was surely a lot to talk about. And, this doesn't come necessarily easy unless you understand what exponentiation is. And I know I jumped around a whole lot. It's really to get you the good idea of what's going on and how you study for these kinds of things. And I know there were some hiccups along the way, but please, go back to these things and say whether or not, I said I'd do like 40 problems, and really I did. And here were some properties there. Had some properties of these things right here. Hope you know those, and really working through the rest of them. Y equals AB to the x. Okay, good old wrap up, exponential growth versus decay and linear growth, interest, compounding interest, all these things. Man, there was a lot to talk about here. So, great review. That's my wrap up, and good luck with all that you do with this material. Fiend!